Welcome to this meeting, this RAS Specialist Discussion Meeting. As you can see from the screen, I hope, there's a banner there advertising the benefits of joining the RAS. And for those of you who are not members, who are not fellows, I really do recommend that you do become one. There are all these benefits. With that, we'll go to the point of this meeting. And sorry, that's on this slide. As questions come up, everyone, if you could use the chat function in order to ask things of the speakers, and the chair and deputy chairs for each session will do their best to keep up on top of the questions as they come in. We'll also ask the presenters if they themselves can patrol the chat function and answer as many of them as the questions as they can after the presentation. And we'll have a record of that. So just to bear in mind, this is being recorded. If we have a problem with video, we do have some of the presentation slides and we would try and show them on the presenter's behalf and ask them to speak to them. Any other failure, we'll try and sort it offline and move to the next talk. I just want to say something about what this meeting is about. It's called Space Weather and the Solid Earth, the Hazard to Technology at the Earth's Surface. And it's basically based out of a NERC Highlight Topic Consortium Award called SWIGS, Space Weather Impact on Ground-Based Systems. And you can see the logo for this project in the top right-hand corner of the page. This is still about improving our scientific understanding of the physics, the space physics, geophysics, driving the ground effects of space weather via surface electric fields, telluric fields, and also understanding the impacts on grids, pipelines, and potentially railway systems. It's now followed by what you might call an implementation project funded by the UKRI Strategic Priorities Fund called SAGE, which is swimmer activities and ground effects. And many of you will have heard of the swimmer program. And that really is to deliver operational services via the Met Office Space Weather Operations Centre. Now, some of the presentations and posters today are from SWIGS partners, and some of our more wider external stakeholders will be joining the meeting. So I'm very pleased to welcome them. And I'm very pleased to welcome everyone to this meeting. Session 1 will be chaired by Juliane Hübert, my colleague of mine at BGS. We'll have a 10-minute break, and then Neil Rogers from Lancaster University will chair session 2. Neil will hand over to Gemma Richardson just before lunch, a colleague of mine again at BGS, to introduce the 2-minute lightning presentations of the poster presenters. And we'll have a lunch break between 1 and 2 when you can view the posters, talk with the poster authors via the GatherTown web tool, which you should have the details of, and Gemma can maybe explain more come the time. At 2 p.m. we'll reconvene on Zoom in this hall, so to speak, and I'll chair the final session, and we'll close. If we've got some time, then we might have a short discussion around some of the meeting's main themes on the ground effects of space weather. And we will have that discussion, should it arise, as I say, because of time, with 3 keynote speakers today, one being Lisa Rosenqvist, our first speaker this morning, of the Swedish Defence Research Institute, Matt Allcock of the EDF Energy Group, this is Chigomezyo Ngwira, presently with ASTRA and also at the Catholic University of America, and he will give us a US perspective on current developments in this area. Both the agenda and the abstracts have been recently updated, and you may wish to refer to the RAS website for this. At that point, since we're now 10:35 or thereabouts, I will stop screen sharing and I will verbally hand over, so to speak, to Juliane Hübert to chair the first session. So over to you, Juliane.
Thanks, Alan. Also, good morning to everyone from me, from my home in Edinburgh to all your homes, wherever you are right now. And we have our first session in the morning with 2 talks. And the first one is by our invited speaker, Lisa Rosenqvist, who works with the Swedish Defence Research Institute and together with the Swedish government's Civil Contingency Agency on the space weather hazards in Sweden and in Scandinavia. And Lisa will provide us hopefully with an overview of what's happening in the northern region of Europe and the implication for risk management in that area. And Lisa, you have half an hour, and I will ask you to maybe share your screen and share video if you'd like, or you can also switch it off if you think it's better for your internet connection. And you have half an hour, we have half an hour for the talk, so it would be nice to have 5 minutes in the end for questions. And people can put their questions into the chat, as we said, because that will allow us to also answer them once the time is up, and they will be there for everybody to see. You can also use the Q&A, but I think we have agreed that it's maybe better to have it in the chat so we don't lose any of them. And Lisa, I will give you a little warning when it's 3 minutes to the end of your talk. Okay, thanks. Lisa, can you say something? I'm afraid we can't hear you.
You unmute your microphone, please.
Lisa, can you mute and unmute? Can you try that? Or maybe try to, if that doesn't help. Does it help? No, it didn't help. I think one way that it could work is if you leave the call and enter it again.
Can you hear me?
Wait. Yes, I can hear you now. Perfect.
Oh, excellent.
We can
Okay.
hear
Oh,
you. Thank you.
okay, great. So I'm afraid my video doesn't seem to work, but now at least you can hear me. Okay, so today I will present some work conducted during the past 5 years in a project funded by, as Juliane mentioned, the Swedish Civil Contingency Agency on modeling and verification of geomagnetically induced currents in Sweden. So first of all, I would like to give some, if this works, sorry. I would like to give some background about the interest in space weather forecasting in relation to the underwater department where I work for research for military applications about the effects from space weather. And this is that due to space weather, we live in a time-varying electromagnetic background noise here on Earth. And it's very important to be able to characterize the variation and strength of this background noise for detection of anomalous fields in various electromagnetic underwater sensors. And for the Swedish Marine Forces, this is very important to evaluate the threat for these electromagnetic sensors, for example, in mines or surveillance systems for naval ships, both for submarines and surface ships. And Dolores Knipst once gave a historic example of this, which related to the self-sterilizations of a whole minefield during the Vietnam War due to a very extreme solar storm. But as you all know, the space weather also drive currents in large conductors, such as electric power lines. And as this figure shows, GICs pass through the coils of the transformers and into the transmission lines. And in cases of very extreme strong currents, this can lead to different problems in power systems. So turning to the vulnerability of the Swedish grid, earlier studies from the Swedish power company show that the Swedish power system is mostly unaffected and very robust for most geomagnetic disturbances. And actually only for very extreme geomagnetic disturbances, there is a hazard of effects in the Swedish power grid. And such conditions occur about 1 to 2 times during the Sun's 11-year solar cycle. Earlier studies in Sweden also show that the largest risk for GIC is in southern Sweden. And this has been explained by a lower conductivity in the upper bedrock layer in these regions, but also coastal regions have been identified as potential hazard areas as the electromagnetic propagation is affected by the increased conductivity in the nearby seawater. And in order then to reach further understanding about all these physical processes that contribute to severe effects in the power grid in Sweden due to major solar storms, the Swedish Contingency Agency financed a 5-year project starting in 2016. And it consisted of a consortium of 3 different institutes studying different parts of the space weather chain. So Stockholm University focused on the first parts of the chains in terms of the solar eruption and trying to reach increased understanding about the magnetic fields in the eruption. And then the Swedish Institute of Space Physics in Uppsala studied the evolution of the CME across the interplanetary space and also the magnetospheric dynamics in terms of energy transfer in the solar wind magnetosphere ionosphere system. While we here at FY studied the end of the space weather chain in terms of the GIC and the effects of the specific Swedish conditions in terms of local geology. So first of all, we tried to investigate what do we need? What are the necessary components to enhance the capability of GIC modeling in Sweden? So we found in literature that the geomagnetic sampling rate is an important factor, and also the spatial coverage of geomagnetic observation is important. Literature has shown that magnetic disturbances that drive extreme GICs can be highly localized, and increased knowledge about how the regional variation of strong magnetic disturbances affect GIC magnitude has been studied in work package 3 of this project. But secondly, also the Earth conductivity models have been identified as a very large source of error in GIC predictions and modeling. And differences between models have been shown to be up to an order of magnitude uncertainties or even larger. And also the assumption of 1D conductivity structures varying only in the vertical direction is inaccurate in regions where we have large lateral contrast, such as in coastal regions, for example, where you go from a low conductivity land to a higher conductivity water. So we have tried to study if these findings from the international community is also valid in Sweden. So here we show the ground properties in Sweden in the figure to the right, which shows the conductance in the upper ground layer in Sweden according to the so-called SMAP model. This model is based on historical magnetotelluric measurements and geological information from Scandinavia, and they have gathered all this information into this map. And looking at this map, we see that there are rather large variations of the ground properties in across the country. And the ground conductivity actually varies by 3 orders of magnitudes, which means that the conditions for GIC in Sweden change considerable between different regions. We have also compared different models in different regions, and we show that there are large differences between these models up to an order of magnitude, just as has been shown by the international community before. Also, many earlier studies, as we have mentioned, assume a 1D conductivity structure with only variation in the vertical direction. But as you can see from this map here, we have very large lateral contrast in Sweden, both in terms of in the southern parts of Sweden, we have coasts at both sides, going from high conductivity in the water to rather low conductivity in southern Sweden that we have already pointed out. That's where southern Sweden is a hazard area for GIC. And the local variability across the country is also high. So that's why we wanted to, in this project, investigate the effects of these two facts, that we have high local variability, large lateral contrast, and also in southern Sweden we have these the existence of coasts on both sides of this region. And we want to investigate the effect on the geoelectric field amplitude in this region. So that led us to development of the so-called GIC SMAP model. It's developed with a commercial software, COMSOL, and it uses this full 3D conductivity model based on the crustal conductivity from this SMAP that I showed before, containing also the surrounding oceans. And from the results that you see in the figure in the bottom right panel here, we get geoelectric field maps of Sweden. And from these maps and observations of the magnetic field variations, it's possible to derive GICs along any arbitrary chosen path according to the shown equations in the box here. And the results show a clear enhancement of the geoelectric field at conductivity gradients, both inland, up here in the Skellefteå ore region, where you have very high conductivity, but also down in southern Sweden at the coastal regions here, both at the west coast, which is more dominant since you have a higher conductivity in the water here, but also in the eastern coast, where you have the more brackish Baltic Sea. So we see that we have a dominant coastal effect here due to these 3D effects. We actually have also verified this model with observations on two different transmission lines. One in northern Sweden, located here, which across the Skellefteå ore region, so this UL4 transmission line. But also another one in southern Sweden, this FT58 transmission line, which we actually, this location was selected as a result of the modeling here, where we show that in this region we have a particularly enhanced coast effect, and we wanted to investigate with an experiment also the effect of these 3D effects in this region. So first, we show the model verification on the northern line in Sweden. The observed GIC in this transmission line is shown in black. We show both in the spectral content and the time series, the spectral to the left and the time series to the right. And the model GIC based on the GIC SMAP model, along with magnetic variations measured in Lycksele, which was very close by to this transmission line, is shown in red. And we can see that the amplitude between the observations and the model is in excellent agreement. But however, as I have already mentioned before, it was the southern region that is most prone to hazards from GICs in Sweden. So we wanted to validate the model also in this region, which is why we conducted a field trial on also this southern line on FT58 in 2018. And also in this region, very close to the coast, where you have enhanced electric fields due to coastal effect. And here again, the observations are shown in black, and the modeled results with the GICS map model based on magnetic recordings from a nearby magnetometer is shown in red. And the agreement between the model and the measurements are very good. But also here, we wanted to study how the difference between the 3D modeling and the 1D modeling. So we also show in green the results based on 1D modeling, assuming only a vertical conductivity profile. And compared to the 3D modeling, the 1D modeling underestimates the observations with about 50%, as these methods cannot account for the enhancement due to the coastal effects in this region. So unfortunately, though, during both of these field trials, the sun was very quiet, and we know that the hazard to the power network occurs only during severe solar storms. So thus we used the GIC SMAP model to investigate the GIC in this verified southern power line by applying historical magnetic recordings to the model. So we used a list of 13 historical storms from the CCMC validation suite. And also we added the September storm in 2017, as this storm has been extensively studied by our collaborators in work package 3. So these two panels now show the maximum dBdt during each of these 14 storm intervals based on magnetic field data from different magnetometer stations at a similar latitude as this southern transmission line in Sweden. But we also added the results based on magnetometer data from the stations in Sweden at higher latitudes, Abisko, Lycksele, and Uppsala. And it shows the maximum dBdt to the left and the maximum GIC to the right for each of these 14 storm intervals. We have also shown here in color coding preliminary risk levels for dBdt according to a study by Peter Wintoft, and also a very crude GIC risk threshold of small yellow, medium in orange, and large in red, according to results from the Solar Shield project in the United States. We should note, though, that these threshold levels would be network dependent and would change from network to network. What we can see here, though, is that the GIC in the predicted GIC, maximum GIC in this FT58 transmission line exceeds 100 amperes and approaches the 200 ampere specification of Swedish transformers for 3 of these 14 historical storms based on magnetic recordings in the higher latitude stations Abisko and Lycksele. And the 3 storms are the famous Halloween storm in 2013, 2003, the St. Patrick storm in 2015, and the September storm in 2017. So thus, we wanted to investigate were there any impacts in Sweden during these storm intervals. So we got a list of impact events from the Swedish network operators, and we saw that there were actually reported impacts during all of these three storms. As we all know, the Halloween storm led to the famous blackout in Malmö, and the maximum GIC in this southern transmission line that we have calculated based on the magnetic recordings in Sweden occur exactly simultaneously as the blackout onset time at 20:07 UT. Not very surprisingly, since we knew that this storm led to major problems around the world. But also less known, during the St. Patrick storm in 2015, there were problems with the triggering of a transformer in mid-Sweden at this location here, T8 Midskog, due to an unknown reason, but the Swedish power network operators thought it was related to solar activity. And our results in this study show that the maximum GIC in our southern line occurs at the exact same time as this transformer triggering. And the same for the September 2017 storm, a triggering in the same region, T1 Bandsjö here, triggered for an unknown reason. And our results show that the maximum GIC in FT58 occur at the same time as the triggering of this transformer. And we actually show here where we have overlain the Swedish network map on the GIC map model and geoelectric field, that both of these events occur in a region of enhanced electric field due to a lower conductivity in this region, but also we have nearby conductivity gradients in this region and may also have 3D effects here. So turning now to also considering the spatial distribution of the geomagnetic disturbances during these events. Here we show the source equivalent currents based on the image magnetometer network in Sweden and Finland during the impact times for the September storm in the top panel here, and during the impact time for the St. Patrick storm in the top panel, and for the September storm in the lower panel here. And we can see that the impact regions, both for the St. Patrick storm, the impact region is here in T8 Midskog, and the September storm here at T1 Bandsjö, occur at the edge of a region of very enhanced westward electrojet in a rather narrow latitudinal band of 500 kilometers here. So this area where the impacts occur during these two storms is prone to higher electric fields due to both geological conditions as well as large regional activity here. However, probably also the exact location of the impact is related to characteristics in the network. So we have investigated the effect of taking into account this regional variability of the geomagnetic disturbance on GIC modeling by studying the...
Lisa, you have 2 minutes.
Yes, excellent. By the September 2017 storm. By investigating a set of artificial transmission lines in a region where we have very high spatial variability during this storm. So by calculating the voltage in each of these lines, assuming both the same magnetic field, so we have a uniform magnetic field in this region, and comparing that to the calculations assuming a different magnetic field at each node, we can see that differences can reach up to 60% of the total GIC. So it's very important to take into account also this variability to accurately model GICs in Sweden. So thus we have made efforts to include a variable source in terms of the source equivalent current system in the GIC SMAP model, and we are verifying the results at the moment. So to conclude, I just wanted to show you a summary of the outcome of this project, this 5-year project. So these are the main results from all the different work packages. So work package 1 has developed the code for magnetic field characterizations in solar active regions in order to improve CME evolution forecasting. Work package 2 have studied the predicted CME arrival time and pointed on the need to improve these prediction times, as they can be up to 24 hours off. And work package 3 has studied this regional variability and the fact that they can influence GIC predictions by 60%. And our work package has developed and validated this 3D GIC model, which can influence GIC predictions by more than 50% due to the coastal effects and conductivity, lateral conductivity contrasts in the region of Sweden. So maybe and perhaps this model can be a piece in a future national space weather warning system. We will see. And by that, I'm finished, and I want to say thank you for listening.
Thanks so much, Lisa. This was really interesting. We do have a couple of questions in the chat, and I can just read some of them out for you, and you can see if you want to answer. There's one from Mike Hapgood asking if you have looked at the relative strengths of the induced geoelectric fields perpendicular and parallel to coasts. The parallel component may be important as many countries have long infrastructures aligned with coasts, as for example in your map of the Swedish grid.
Yes, that is definitely true. We have not studied that question in detail, but definitely it would be very interesting.
All right, there's a question from Stanislaus Nadi asking, what about severe solar storms and how was the GIC risk threshold derived?
We have made a study on a very extreme storm due to called perfect interplanetary CME. So more or less the worst one can expect hypothetically, and that has been Daniel Welling has made a model run with the CCMC model, or BATS-RAS, and we use that result into the GIC SMAP model to investigate how large GICs we would get in this southern transmission line, and they would be quite large, only due to this sudden storm commencement up to 400 amperes. What was the last part of that question? Sorry.
It was about the thresholds for the GIC.
Oh, the thresholds, yes. The thresholds, the BDT thresholds, they have been made by comparing impacts in Sweden. This impact list that I talked about that the Swedish power grid operator has handed out, and comparing that to the DBDT in the Swedish magnetometer network during these impact times. The GIC thresholds, they were just really taken from the Solar Shield project as between what do you call it, very crude thresholds for small, medium, large GIC. But as I mentioned, this would be very network dependent and has to be derived for each network separately. So it's only very rough indication on if they are small, medium, or large.
Thanks very much. There are 2 more questions in the chat, Lisa, and if you have the time, you could just read them and answer directly in the chat. And we will pass over to the next talk, which is by Stefano Maffei, a Swiss collaborator at the University of Leeds. And this talk is entitled "The Future Location of Auroral Zones as Described by the Geomagnetic Field of Internal Origin." And Stefano, you have 20 minutes in total, and I just give you a warning at 12 minutes, so you know that you have 3 minutes left, and then we have 5 minutes for discussions.
Yeah, okay. Can you confirm you see the full screen presentation, not the presenter?
Yes, I can see the full screen.
Excellent. Okay, thank you. Thank you very much for the introduction. So yeah, I'm going to present in this presentation. I'm going to talk to you about some early results from a project that we are performing at the University of Leeds about linking the evolution of the geomagnetic field of internal origin, and by that we mean the component that is generated in the Earth out of the core, with the space weather relevant quantities. And in this case, we've focused on the auroral zone evolution. I'm going to better define what I mean by that. And what we want to obtain is this kind of forecast. So for example, in this picture is the auroral zone on the North Pole between 2020 and a possible forecast for 2070. This work is performed mostly by me, Phil, and John at the University of Leeds, and in collaboration with Mervyn and Jonathan at BAS and ICL. So okay, let's take a step back. So the auroras are essentially generated by the interaction between the geomagnetic field and the solar wind, essentially. And the auroral oval is defined as the region where around the poles where it's most probable that you would actually see auroras, which are caused by the precipitation of solar particles along the magnetic field lines, which are mostly dipolar in shape, and down to the upper atmosphere where they interact with the atmospheric particles and generates visual light, essentially. So there is 2 components in where the auroral oval are and what their shape is. One is the geomagnetic field itself, which controls where their general properties, like where on average they're supposed to be, and the solar wind, which depending on how strong it goes, it can make a larger or a smaller auroral oval. Yeah, this is the definition, and this definition is the second one I used of the auroral oval. Another possible definition of auroral oval is in terms of the energy that the solar particle needs to penetrate down to the upper atmosphere. So what we are actually interested in is an average description of these. So as the solar wind represents somewhat the weather component of the auroral oval, we're interested in somehow describing the climate. So a description that is valid on at least multi-decadal timescales that maybe loses something about the details of the event by event shape of the auroral oval, but on average will tell me, depending on the magnetic field structure, where am I most likely to find the auroral zone. So the auroral oval. So I'm using the auroral zone in this sense. And a definition of the auroral zone is can be this. So it's essentially the auroral oval, only the night side component of the auroral oval. But again, we are going to be mostly interested in this description, so a multi-decadal average of the oval. I found that this is not a unique definition of the auroral zone, and this is not my area of expertise, shall we say. So please feel free to call me out on my use of this definition in the questions. But this is what I'm going to mean in the rest of the talk anyway. So in general, what is usually done is to describe the auroral zone as a circle, as a ring, centered around a pole that you have to choose, and typically with an amplitude that goes between 65 and 70, depending on the brightness you pick as the significant boundary of this zone. While this is a perfectly valid description in case of, for example, it has been used in studying the auroral zones in pre-observatory era, so before we had a direct observation of the geomagnetic field, and therefore the information about the geomagnetic field itself were limited. Today, we have more information about the geomagnetic field that allow for a more elaborate, let's say, description of the auroral zone that is not just a ring. In particular, is not an easy question to ask yourself, what is exactly the pole you want to center your zone around? Because normally you would mean the geomagnetic dipole, which is essentially the where the dipole axis intersects the surface of the Earth. However, some people have questioned whether we should use the dipole, which is where or magnetic pole, which is where the compass points downwards. And because the geomagnetic field is not exactly a dipole, and in particular, you see in the northern pole, there is this complicated two-lobe structure that changes in time. The dipole and the geomagnetic pole can be quite far apart from each other, so your ring will be centered around very different location. And also their temporal evolution is very different, as you can see. And maybe you know in recent years there has been big news about the magnetic pole, moving the north magnetic pole moving very fast from Canada toward Siberia, while the southern magnetic pole didn't do nearly the same. So to describe, so we want a description of the auroral zone that in particular does not require me from choosing a pole. So instead of presenting you the past literature on how this can be done, I'm going to show you an observation that I hope justifies the approach we use here. And this is, on the left panel, you see images of the pictures of the auroral ovals from the image satellites from 3 different instruments. And you can note, now I'm going to be qualitative on this, but you can see that the auroral oval actually can be described as a circle, but if you choose the right coordinate system, so in particular in this CGM coordinate system, you can roughly describe the auroral oval and by extension at its time average as a circle. So what we do here is to calculate a conversion between geographic and CGM coordinates. And these CGM coordinates as an input take a model of the geomagnetic field. So we can simply give the past, present, or a forecasted geomagnetic field model and define the auroral zone as the 65 to 70 magnetic latitude. So in this coordinate system, not in geographic coordinates. So we've done this. In particular, we've used this Python wrapper for an older C++ routine, well, not that old, proposed by Shepard in 2014. So this calculation is performed with the IGRF13 model as an input for the geomagnetic field coefficients. And here we calculate the 1950 and 2020 auroral zone, and this diamond marks the geomagnetic pole, although it's not, again, it's not explicitly used in my definition of the auroral zone. Very qualitatively, we compared, and notice this is Canada, which is also here in these figures on the right. We qualitatively compared our method, our results with results from a completely independent method, in particular make use of magnetospheric conditions, so they take into account the weather as opposed as purely the climate as we do. And there is some satisfactory qualitative agreement in our opinion. We have to do some more quantitative testing, but this gave us confidence that our method, that this method can be used to forecast the auroral zone in the future. But for that, we first need a forecast of the geomagnetic field. So we use, this would be a special discussion by its own, so I'm going to be very quick about this. We used only two available forecasts that are out there. One is this data simulation that we call the IPGP forecast because it's been from the institution where the main author sits today. These forecasts has been generated by essentially the same methods that give us weather forecast. So we use, the author used a geodynamo code, which models the dynamics in the Earth at the core where the geomagnetic field is generated and correct the evolution of that code by available observation. By doing this up to the present, where the observations are available, you hope that you are correctly describing the outer core, and then you can just evolve it in time to obtain your forecast. One result of this forecast in particular is in agreement with virtually every other forecast that is out there, and this is that the current upward intensity trend is likely going to continue in the next few decades. There are severe limitations to this approach, however, because these are extremely complicated models that likely do not operate because of computational limitation in the same parameter space as the true Earth. In particular, we usually refer, we depict this divide in terms of the viscosity represented by the Ekman number on this axis. And there are order of magnitudes between what we think the real Earth core is and the simulation used for this kind of forecast. While this doesn't seem a problem to forecast the dipole components or the large scale part of the geomagnetic field, there might be problems for smaller, other components of the geomagnetic field that describe smaller spatial scales. This is an example taken from a different simulation, but the result is very similar. So the data simulation can diverge quite a lot from observations. This is an example where the authors try to predict the path, so they have observation available to compare. And in particular, you see that even a linear forecast, so a linear extrapolation of this coefficient sometimes does a bit better because of this limitation. Even if you're hoping that this method captures the dynamics and therefore is more accurate. So another forecast we're using is exactly this. We use the IGRF forecast that is designed only to forecast the field for 5 years. We just use it to forecast for the next 50 years, which is not completely accurate. It's not what it's designed for, but we showed that it might still be reasonable, also given the evolution of the geomagnetic field coefficients for the past 50 years. Here I'm showing the dipole component, the quadrupole component, which are described by these spatial shapes, and liquid 4 components, which are describe the shape of these spatial features. The dashed line represents the IPGP data simulation forecast, and you see these may diverge quite a lot. Anyway, we calculate CGM coordinates for these two forecasts, and we obtain these results for the IPGP forecast. We see that the trend is of movement of the auroral zone is going to continue in the future. What's interesting is that you see that the auroral zones are very different between the south and the north pole, confirming that non-dipolar components of the magnetic field play a role in their shape and evolution. A forecast based on this simple linear extrapolation model is more significant because because of the forecast tells me how the coefficients are going to evolve in the future, but they're qualitatively very similar, right? So this general movement of the zone away from North America and towards Siberia seems to be continuing in the past, in the future. Another interesting thing we can do, so we have focused on the auroral zone now. a space weather relevant thing we can look at is this latitude danger. We call it the danger zone latitude between 50 and 60, which has been proved to be where you expect to see the most damage for a very big 200-year return extreme solar event. And this is roughly where the UK sits today. So we use the same technique to forecast where these danger latitudes would be in the future, and we obtain for these two forecasts this picture. So 2020 is the orange and 2070 is the forecast. And you see, I don't have time to describe all the details that you can deduce from this map, but interestingly, you see that these danger latitude will not change much for the UK in 50 years, nor for New Zealand, for example, which is also at similar geomagnetic latitudes than the UK. However, there are quite some significant changes for Canada. In particular, you see that Newfoundland and big cities like Quebec City and Montreal will find themselves below this danger zone, and also while cities in North Europe and Russia will progressively get into it. Yeah, this is so my summaries of what I just told you. I'm just going to mention some work in progress, which is, as I mentioned, more quantitative testing of this technique. I've been very qualitative because these are early results, but we can definitely properly test the error we are committing, and maybe extend our methodology to be able to more predict the weather. So given a specific solar event, how the day side of the oval is forecasted. Another interesting thing we want to do is corroborate our methodology for past events. So for example, for the Carrington event, which is this very, very big event that happened in 1859, what was the danger zone, which likely is applicable to this event, and whether the damage at the time was mostly found in that region. So whether that definition in our technique is relevant. And yeah, thank you for your attention, and I'm happy to take questions.
Thanks, Stefano. That was right on spot, 15 minutes. There was a little bit of a confusion about how to use the chat, and everybody should have the ability now to direct questions into the chat to everybody or to specific people, and also to read all the answers. So if people could type their questions into the chat for Stefano right now, that would be very helpful.
Should I read them, or should I stop sharing?
If something pops up, I can read them out to you.
Oh yeah, thank you.
Right now I can't see anything. There was one general question, sorry Stefano, that was about if slides and presentations will be made available, and if we have the permission to distribute the slides and the presentations, they will be made available for all participants next week or at some point after the...
Yeah, sure. I mean, this is being recorded anyway, right? So I'm fine with it.
But still...
Yeah.
Still.
No problem.
All right, we have a question from Maria Wallach. She's asking, I like your definition of weather and climate in terms of auroral oval. Are you planning on including expansions and contractions of the oval as part of your weather forecast and modeling?
So, well, maybe. I mean, this was essentially included in this point. I would say this is not what I'm focused on, because what I'm interested in is describing the evolution of these zones in terms. So that would be a parameterization, right? Maybe we can include it, maybe not. What I'm mostly interested in is connecting the evolution of the internal magnetic field with these quantities. So if that works, sure, we will look at it. But if it's not possible to meaningfully do that based only on the internal magnetic field, no. But yeah, we are going to look into it.
Okay. Again, thanks, Stefano. There's still the ongoing option to write more questions to Stefano into the chat. And we're going to break now for 10 minutes for a little coffee break. You do not have to leave the call. You can just rest assured we're going to convene in 10 minutes, 11:35 for our second session.
Okay.
Welcome to the second session of this RAS specialist discussion meeting. We have three speakers. First is Andy Smith from University College London. And if I could ask Andy to share his screen, and we'll hear about sudden commencements.
Hello, hi there. Just going to check. Can you guys see my screen?
Yeah, that's good, thanks.
Okay, brilliant. So hello, I'm Andy Smith. I'm based at RAL Space Science Laboratory at University College London. And today I'll be talking about the contribution of sudden commencements to geomagnetically induced currents in the UK. Okay, so we're talking about the ground impact of space weather in this meeting. And hopefully the animation is going to play. Yep. And these are all driven by the dynamic and coupled environment between the Earth and the solar wind. On the left-hand side here, we just have a side-on view of an MHD model that is looking at the kind of coupling processes between the two systems. We can see it's quite dynamic and highly variable. And that has consequences for us on the ground. So all of those changes result in the creation and changing of ionospheric currents. These in turn can induce currents on the ground, known as geomagnetically induced currents. And these have consequences for grounded infrastructure, such as power grids and pipelines. On the right-hand side here, we just have a power transformer to scale with a human. So these are quite large and quite expensive pieces of equipment. So we want to take the best care that we can. On the right-hand side, there are some pictures of a damaged power transformer. This was damaged during a geomagnetic storm in 1989 in Quebec, and its damage took it down and out of service, resulting in a blackout for around 9 million people for about a day. So we really want to predict when these currents are going to be present and try and mitigate their impact on our society. In terms of measuring GICs to perform large-scale statistical surveys, unfortunately, they're not normally available, as they require specialist equipment to be measured and specialist analysis. So for long baseline studies, we generally need to use a substitute measurement. To identify what we're going to use instead, we have to consider several different properties. So the magnitude of a geomagnetically induced current will depend on primarily the rate of change of the magnetic field, which I'm going to term R in this talk. And it's a vector quantity. It can vary in different directions. Something that I haven't put on here, but is also important, is the time, the frequency components of that change as well. But we're not going to talk about that too much in this talk. Secondly, as we saw earlier in Lisa's talk, the subsurface conductivity is also crucial. And we have things like coastal effects enhancing the currents around coastlines. And thirdly, the geometry and properties of the power network are also crucial to calculate what currents will be induced. So that's both the geometry, so the alignment of the power network relative to the changing field, and also things like the resistances of the components of the power network. On the right here, we just have a diagram showing the electricity network in the UK. And we can see it's very, very complex with numerous connections and that kind of thing. And each of those adds its own level of complexity. On top of that, I've marked 3 UK magnetometer base stations. These are run by BGS. So we have Lowick in the northernmost part of the UK, Estelmuir in southern Scotland, and Hartland in southern England. And those are the 3 stations from which we're going to be taking our rate of change of the magnetic field. And we're going to be using that as a proxy for GIC strength in this talk. Okay, so the first phenomena that was looked at in terms of what it contributes towards the UK's large rates of change of the field were substorms. Just to take you through this figure from a paper by Freeman et al. In 2019, here they plotted the probability density against R, both on log scales. What we can see is that the black line giving you the total data set, which was about 20 years long, the vast majority of the data is located up here at around 0.1 to 1 nanotesla per minute changes. So during the majority of the time, the field is relatively quiet and doesn't vary too significantly. However, we see the strong power law at all three stations that they've looked at, leading up to larger values of R. So these are still fairly common. What they've then done is they've split up the data set by the phase of the substorm. I'm not going to go too much into the phases and what they mean, but suffice to say the expansion and recovery phases here in light blue and pink are the ones during which we'd expect the auroral currents, or atmospheric currents, to be most active and therefore potentially see the largest GICs in substorms. What they've done is they've split up the data set into those different categories. And then in the lower panel, they've divided these through by the total data set to get the proportion of each phase that contributes at a given level of magnetic fluctuation. And what we can see is that at all three stations, the other times in orange dominate at low R. So between 0.1 and 1 nanotesla per minute changes, we see this other times, so unrelated to substorms, contributes over 90% of our rates of change. What we also see is that during the expansion and recovery phases, here in dark blue, they become increasingly important as R increases. So above 10 nanotesla per minute, roughly, we find that around 50 to 60% of our large rates of change are accounted for in these phases of a substorm. So to summarize from that, approximately 50% of large R is associated with substorm expansion and recovery phases. And I'm using large R here to mean something of the order of 50 nanotesla per minute or so. So of the kind of level that we would start to generate significant currents. However, that does leave 50% of large R in the UK unaccounted for. So we then went to look and see if there were other processes that we could determine were important in generating these kinds of levels of magnetic fluctuation. So the process that we chose to look at is called a sudden commencement. On the left-hand side here, we have an MHD model output looking at the equatorial projection of the magnetosphere as a sudden commencement occurs. The sun is off to the left here, and the color gives you the density of the plasma. And as the movie just reverts around to the start, we can see a high density and high pressure front comes in, and it rapidly compresses the less dense magnetosphere. So this is a global process that occurs. But if we have individual magnetometer stations on the ground, we can actually measure these impacts using them. So on the right-hand side, we have a series of 7 magnetometer stations ranging between 40 degrees magnetic latitude up to around 65 degrees. And we plotted the northward component of the magnetic field. At time 0, so T0 here with the black bar, we can see that the northward component of the magnetic field rapidly increases simultaneously in all 7 stations. So this is the sudden commencement, and generally they last for around 5 minutes, basically as long as it takes the magnetopause to react to this sudden pressure increase in the solar wind. What we can also see is that at the lowest latitude stations, we see the smallest relative increases in the field, and at higher latitudes, we see a larger increase. And this is just for this event, but later on we'll have a look and see statistically if that holds. For context, the UK is located at around these kind of latitudes, so we wouldn't necessarily expect to see the largest rates of change of the field during the sudden commencement itself, but they can still be pretty sizable. The other thing that I'd like to flag in this is that following the sudden commencement, there is often further activity induced by this same pressure pulse in the solar wind. So here we see above a latitude of around 50 degrees, the field becomes very variable afterwards, after these events. So the sudden commencement itself can be used as an indicator that further activity might be likely. So our question is, how much do these sudden commencements actually contribute towards the large and extreme rates of change of the field in the UK? Okay, so here we've got each of the 3 stations on its own panel, increasing in latitude going from left to right. And we plotted the percentage of data that is related directly to a sudden commencement as a function of R. What we can see is that at our lowest latitude station here in green, a maximum of around 8% of the data exceeding around 50 nanotesla per minute is directly caused by sudden commencements. So that's those few minutes just around the impact of the pressure pulse. As we increase in latitude, that drops to around 4%, and then it drops to around 1% at our highest latitude station. So overall, these things don't contribute that much in the UK, but there is a clear latitudinal trend. If we include the 24 hours that follow the sudden commencement, so this is including things like shock-induced substorms or storms, then we find that we can then actually attribute around 70 to 80% of our rates of the change of the field, exceeding about 20 nanotesla per minute, to these phenomena, or to that period of time, rather. And if we play that same game again, increasing it to 48 hours, and then to 72, we can find that around 90 to 95% of our rates of change of the field exceeding 20 nanotesla per minute are associated with sudden commencements and the 3-day interval that follows. So it's quite a broad window of time, but considering we used 20 years worth of data, and there were around 350 events in that time, they're actually quite a small subset of the data themselves, so that the fact they contribute so much is interesting. Sudden commencements can also be classified into two broad categories. So in the top here, we have those that are classified as storm sudden commencements. So that means there was a geomagnetic storm within a certain number of hours, I think it was about 12 hours in this study, of the actual impact. And if there is no geomagnetic storm, then they can be called a sudden impulse. And in this work, our events roughly split equally into these categories. So we're down to around 180 in each bin, roughly. But what we can see is that these panels in the top strongly resemble the ones on the previous slide. So only the storm sudden commencements are really contributing towards the large rates of change in the field. And the sudden impulses don't really contribute much in terms of percentages to the large rates of change of the field. So we've gone from our data set of around 350 events, and roughly half them, and these are the kind of at-risk intervals for the UK to see these large rates of change. So that was our UK-based study. But the question that we had coming from this is that we've seen a clear latitudinal difference between the stations in the UK, even though that's only about 10 degrees worth of latitude. So what we wanted to do is then expand that and see if these results are more broadly applicable to, for example, other stations in Europe, or how it changes going from the magnetic equator up to the northernmost stations that we have in Europe. So we selected 12 magnetometer stations, ranging from our northernmost, which is about 65 degrees latitude, all the way down to a couple of stations near the equator, of the magnetic equator. And what I've done here is we plotted the probability density as a function of R again, and the color of these traces gives you the magnetic latitude of the station that we're considering. So for example, these blue stations, blue and purple, are the lowest latitude stations below 10 degrees, and we see that their power law distribution drops off much more rapidly. So they are much less likely to see large rates of change of the field of the order of 100 nanotesla per minute. However, at the higher latitude stations in red, we see the power law drops off more slowly, and therefore they're much more likely, just over our statistical data set, to see large rates of change of the field. If we then narrow that data selection down to those times just during sudden commencements, so in total that's about 1800 minutes in our entire 20-year data set, we find that again we see a similar pattern where the lower latitude stations generally see smaller rates of change of the field. And then as we increase in latitude, these curves shift towards larger R. So this tells us that the sudden commencements are larger at higher latitudes, but also that those stations are more likely to see large rates of change of the field. So how does this affect our percentages that we can attribute to sudden commencements? On the left here, we plotted the percentage of R exceeding a given level that can be related to a sudden commencement as a function of R. I've now switched to a log scale on the y-axis here, just to separate out these traces a bit. And what we can see is that at the lowest latitude stations, at around 50 nanotesla per minute, we've got about 20 to 30% of our data that can be directly attributed to sudden commencements. As latitude increases, this drops quite dramatically until by the time we reach around 50 to 60 degrees latitude, we're at much more like 1 or 2% of our data. And at 60 or 70 degrees, we've got a much smaller fraction. If we split these down into storm sudden commencements and sudden impulses, then we can see that we're entirely dominated in our percentages by these storm sudden commencements. So this tells us that sudden commencements are more important at lower latitudes. The sudden commencements themselves are smaller, but the rates of change of the field are smaller at those latitudes anyway. So fractionally, they are more important. To look at the days after, I'm going to take a cut through at 50 nanotesla per minute. And this just lets us view the results in a slightly more quantitative fashion and it's a bit clearer with so many stations. So in the top left here, what we've done is we've taken the cut through 50 nanotesla per minute, and as a function of latitude, we have the percentage of data that exceeds that threshold. And what we can see is that at our lowest latitude stations here, we have around 20 to 30% of our data that's explained by sudden commencements. And this drops off roughly linearly with the latitude until we reach around 55 or 60 degrees, at which point they become almost negligible. If we add on a day to our data, so we're looking at sudden commencements and a single day afterwards, we find that we can explain around 80% of large rates of change of the field exceeding 50 nanotesla per minute. And again, we still have a rough linear trend here. And then at around 55 or 60 degrees, we see the sharp drop off. And this must be as other processes, such as more isolated substorm activity, is contributing a much more significant fraction of our large rates of change of the field. And as before, if we include the second and third day, these percentages increase roughly linearly. And we find that around 95 to 100% of data exceeding 50 nanotesla per minute is explained by sudden commencements and the 3 days that follow. And again, just to reiterate, if we split them into storm sudden commencements and sudden impulses, we find that it's just the storm sudden commencements that are important in this time. And in fact, we can see the kind of effect of substorms here, in that these points here are actually shifted up slightly, more significantly than any of the other points in this graph. Okay, thank you. So just to summarize, for the UK, 50% of extreme R in the UK can be attributed to substorms. Less than 10 or 8 to 10% of extreme R is directly attributed to sudden commencement intervals. However, greater than 90% of the extreme R in the UK is within 3 days of a storm sudden commencement. If we expand this to other locations, at equatorial stations, sudden commencements are very important, even though they themselves are quite small. And above 60 degrees latitude, sporadic and isolated processes, such as substorms, become much more important. And that's my talk. Thank you very much for listening.
Thank you, Andy. I think we had just one comment from Juliane. I don't know if you wanted to unmute and say anything more about the replacement of transformers.
Yeah, I was just going to say it's actually in the UK risk register published by the Cabinet Office. There's quite a lot in there about the problems that could occur because obviously these transformers are several hundred tons each, and I think there's only in Europe there's only about half a dozen manufacturers and producing a few dozen a year. And if you see them going up and down the road, you know how big they are and how difficult they are to move. And obviously there's no spares apparently, or very few spares. So the danger is if it does get out of control and they don't shut the grid down in time, that we'll lose too many transformers and end up with a long blackout.
That's a very good point, definitely.
Don't know if there are any other questions. People just want to raise a hand or put it in the chat. I have one question: is sort of how do you define the sudden commencement? How long a period do you define after the sudden commencement to actually count it as a sudden commencement?
So generally, I've done this observationally. So looking at when the station starts to respond to the pressure pulse, you see the increase in the northward component, and then it increases for a certain amount of time. It's like an impulsive step. And then it starts to stop, and then there's other things such as wave phenomena that start to come in. But I generally stop it at the end of the impulsive phase. I'm not sure if it's technically called an impulsive phase, but basically the start of the main increase.
Yeah.
It takes a couple of minutes.
Okay. Yes, one more comment from Mike. But, I think we have probably time to move on to the next speaker. Thank you, Andy.
Thank you.
Next speaker is Carl Haines from the University of Reading. And hopefully, Carl, if you just unmute and please take it away and take away your talk, please. Cheers.
Okay, sure. Okay, so today I'm talking about temporal downscaling. So that's increasing the time resolution of a data set, and I'm looking at magnetic field data. So the problem that I'm addressing is that we want to be able to forecast GICs, And for that, we need an accurate electric field input. And to obtain that, we need a high time resolution magnetic field. Where we would get that magnetic field forecast from is something like SWMF. And we've got a plot from that here. And what we see on the plot on the left, where black is observations and red and yellow are model outputs, is that the model's not really capturing the high time resolution perturbations. On the right, we've got the power spectrum showing that again, where the model is underestimating the power of the higher frequencies. So why this is a problem is because in the green box, so we're interested in the electric field on the left, and it's equivalent to the change in the magnetic field. So to really hammer that point, on the right is a cartoon plot that shows the red line, which is very smooth through time. It's something like what the SWMF would output. It's a bit of an exaggeration. But what we see is that because there's a low resolution in it, we don't get the variability on a higher time frequency like in the yellow line. And so we would expect an underestimation of the magnetic field and of the change in the magnetic field and of the electric field. So the goal of this project that we're working on is to increase the time resolution of magnetic field data so that we can use that to get a better estimate of the electric field. So what I'm going to do in this presentation, doing my project, is take some magnetic field data. That will be from SuperMag, and I'm going to give a proof of concept that we can increase the time resolution and add realistic noise. And I'm going to show that that is valuable. So the data I'm using is from the Estelmuir site with 1 minute resolution. However, the model I'm showing is theoretically valid at any location where we've got a historical high resolution data set. So what I'm going to do is I'm going to take the hourly means of the magnetic field, and that's going to be my model-like forecast. So that's going to be similar to the SWMF. And that gives us an hourly resolution time series. We're going to then try to reintroduce minute scale noise with realistic variations. We're going to do this through downscaling, and we're going to put that time series through a model, an MT transfer function given to us by BGS, so that we can see whether doing the downscaling gives us a better estimate of the electric field compared to not doing the downscaling. So really for us, a good outcome is that we get a better estimate of the electric field. So my algorithm I'm going to use is the analog ensemble. This has been known as a similar day approach, and I'm just going to take us through it in 4 points as to how it works. So we take a low resolution forecast on an hourly scale that's represented by these 2 dots here in red. We then look in a historical data set which has high resolution. So we use our the SuperMag 1 minute data set, and we look for a similar period as our forecast. That's ovaled, circled here. We found an analogous period, we call it. We then zoom in on that analogous period and we see the high resolution noise on the minute scale. And we lift this noise and we add it on to an interpolation of our initial forecast. So in that way, we have increased the time resolution of our forecast with realistic noise. Now, what we did here was we found the best analogous period in a historical data set, but the way we've implemented this is as an ensemble. So we found the best 100 analogous periods, giving us 100 high resolution downscaled time sets. and we can use this as an ensemble. So this is showing an implementation of that for a particular time over about 6 hours. These are two components of the magnetic field. What we see is the observations of what actually happened are in red. The black shows the median of our analog ensemble, and the color bands show the spread. The light gray line, it's in the legend as upsampled, is simply a linear interpolation between the hourly points, such that it becomes a data set on a minutely resolution, but it has no noise. So this is our our do nothing approach, which is the benchmark for our downscaling scheme to beat. And so far we see that our downscaled time series looks much more realistic than the do nothing approach. However, it is obviously not equivalent to observations, typically being a bit of an underestimation. So how do we evaluate this? Well, the purpose, as I mentioned before, is to better drive a model of the geoelectric field. So we take the observation time series, the downscaled, and the reference do nothing approach, and we run this through the MT transfer function from BGS to give us an estimate of the geoelectric field. So we've done that here. The colors are the same as before, but instead of this plot representing the magnetic field, it's for electric field. What we see is that the analog ensemble, again, is a better estimate of the electric field than the reference approach. However, on the whole, particularly for the median, we're certainly underestimating the electric field. So next, I'm just going to move on to try and show whether or not the downscaling is useful for event prediction. So what we've done is we've defined an event that we want to forecast as the 99.9th percentile in the data set, the whole data set of the electric field. And we say a single threshold crossing is classed as an event. So that could be just a single minute. So to do this, we wanted to be robust to timing errors. So that would be where the analog ensemble predicts an event, but it's at slightly the wrong time. So maybe just a few minutes out. Under some metrics, the analog ensemble would receive a double penalty for this because it would be penalized for predicting an event when there is no event, but also for not predicting an event when there is one. So for this, we use the fraction skill score. This counts how many events that we predict inside a time window. For us, we've chosen this as 1 hour. We count how many events are actually observed within this time window, and we compare the two. We find the error. We repeat this process for the reference forecast, which is our upsampled do nothing approach. And then the fraction skill score is just 1 minus the quotient of the errors. So on the right is the results of the fraction skill score for each of our 100 ensemble members. We see that, the fraction skill score, 1 would be a perfect forecast, 0 would be unskillful compared to the reference, and you can be negative if the reference forecast actually performs better. So we're seeing that all of our ensemble members are having positive skill, which is very good, we're very pleased. And it's showing that the analog ensemble is outperforming the reference approach. The mean here is 0.414, which is positive. You'll notice that ensemble members with a lower ensemble ID typically receive a higher fraction skill score. Now, this is because during the training of the model, the best analogs are associated with the ensemble members with lower ensemble IDs. So what we're seeing is that a better analog gives us a better downscaling. It gives us a better output. So this can help inform us on the appropriate ensemble size, but it can also serve as a weighting for when we are converting this ensemble into probabilistic information. So in summary, we need high resolution noise in magnetic field data in order to drive models of GICs. We have developed an approach that adds realistic noise so that we can increase the time resolution. And when we use this to drive some sort of impacts model, the electric field model, we received positive skill and we outperformed the reference approach. So what we're going to go for next in this project is pretty much do it better. So what I've shown here is a proof of concept study, but we will then look to improve upon what we've done, more sophisticated techniques and the use of other predictors as well as just the hourly mean. So thank you very much. I'll be happy to take any questions if there are some. Good.
Yeah, thank you very much, Cole. If anyone's got a question, they just want to raise their hand and I can unmute them. Otherwise, I have a question. Do you think that your analog ensemble technique could be applied to other fields of research? Have you come across any other fields that could be used?
Yeah, so it was originally developed for terrestrial weather forecasting back in the 70s before physics-based models really took over. So that's sort of where we got it from. Initially, my supervisor, Matt Owens, has used the analog ensemble for solar wind forecasting. And I myself has used it to forecast geomagnetic activity in the AAH index.
Okay, great. We had one hand up from Alexei Kushinov. I don't know if you want to unmute.
No, it's my bad. I'm sorry.
Okay, no problem. Another question from Stefan. He says, nice talk. And similar ideas were used by Owens et al. For solar wind data. He gives a DOI, so something to look at there. I don't know if anyone else has seen any things in the chat. So if not, we've got a few minutes if anyone wants to ask a question. I can't see any, so I will just thank Carl again, and we'll move on to our next speaker, if that's okay. So our next speaker is a keynote speaker. It's Matthew Allcock, and Matt is a natural hazards research engineer and space weather specialist with the Environment and Natural Hazards Group at the UK R&D Centre of EDF Energy. And we're hoping Matt will provide a welcome industry perspective to the space weather hazard, so on space weather hazard to ground-based technology. So thank you, Matt.
Fantastic, thanks, Neil. Let me just try and share my screen. Okay, that should be coming through. Please let me know if it's not doing. Great, yeah, thank you very much for the invitation to give a talk here. It's kind of a nice, unique opportunity to give a talk at an academic conference from an industrial perspective. So I guess my my kind of comparative advantage, for want of a better word, here is not to go deeply into the research necessarily, but more to give like a perspective from industry, and in particular the energy industry. And yeah, my aim, I guess, is to focus on the approach that we have in the energy industry to space weather and natural hazards more broadly. what some of the incentives are that we have to kind of fit in with, incentives from, for example, nuclear energy regulators, and maybe what some of the open questions are for space weather in R&D in industry. So yeah, along the way I will give some discussion about some of the research that we've been doing, but there'll be some kind of overview of the different perspectives as well. Great, so yeah, we'll give some context about nuclear energy, EDF, what natural hazards are, and how space weather fits into that. We'll give some perspective from nuclear energy regulators, which are a big part of the incentive structure in the nuclear energy industry. And then I'll give some research, overview of some of the research that we've been doing that helps to characterize the space weather hazard for the nuclear energy industry. Okay, so first let's take a bit of a kind of high-level overview of UK energy. This is from January this year, the mix of energy that the UK are using. So still have kind of a big chunk of gas. Coal has gone down dramatically over the last few decades, and we're seeing obviously big uptakes in wind. The UK is very big on wind because it's a very windy country, but we also have a big chunk from nuclear as well, and this kind of bar chart at the bottom here is showing how our kind of national performance is going in terms of carbon use per unit of energy generated and used in the UK. So this target here is the aim for 2030. So yeah, definitely some progress being made there. A bit more broadly into Europe and beyond, looking at nuclear energy. So this is a map of all of the nuclear power stations in the world. Big cluster in the US, in Europe, and in kind of East Asia, in Japan especially. And on the right-hand side, we've got the sort of infographic of the top 15 nuclear energy producers. So France is a big one here. Like the circles are proportionate to the total power output of all of the nuclear energy reactors that they have in these different countries. France is dominant in terms of its proportion of national energy produced from or generated from nuclear. It's like well over 50%. And the UK is here, so we have a significant chunk, but kind of a bit smaller than some of the other kind of big hitters in the nuclear energy industry. So EDF, that's where I work and kind of who I'm representing today. So it's a company that spans France and the UK with some kind of subsidiary groups across the rest of the world. It's mostly owned by the French government, or at least within France. Most of the French part of EDF is owned by the French government, and sort of operates in a national level there. In the UK, it's a privately owned company and is kind of the big generator of nuclear power in the UK and in France. So yeah, we operate all of the active nuclear power stations in the UK, which is about 8, I think. And in France, there's 20 something, maybe 28 or so nuclear reactors. And there's plans for the future for new reactors that you've probably heard about, Hinkley Point C and Sizewell C being the main 2. So here are a map of kind of the nuclear power generating stations in the UK owned by EDF and in France as well, just to give an idea of the scope and scale of the nuclear industry in the UK and France. So I'm coming to you from EDF R&D, which is a kind of big part of the EDF kind of ecosystem, because we kind of need to stay on the innovative frontier, and especially when it comes to safety. So in the UK R&D, there's kind of 4 teams. I'm in part of the nuclear team with, we have 70 full-time researchers and many PhD students, and we're kind of spread out across the UK. So I'm part of the natural hazards research team, which is within the nuclear team. So natural hazards covers a variety of different hazards that can affect energy infrastructure, in particular nuclear energy infrastructure, just because it's such a safety conscious kind of part of the energy sector. And this graphic gives us an idea of what hazards we're talking about. So everything from kind of meteorological hazards, extreme wind, to kind of coastal hazards, coastal flooding. So a lot of the nuclear power stations are based at the coast because that's where they can get the cool water for the cooling systems in nuclear power stations. Yeah, so I've circled the one up here, space weather. That's kind of what my specialism is, I guess, at EDF, and what the focus will be today in the talk. So natural hazards, the risk from natural hazards are characterized kind of like this. So we sort of see it as a three-pronged approach. So the risk is a combination of the hazard itself and the characterization of that hazard, which involves the probability of the hazard occurring and the severity that you would expect across various timeframes and various occurrence probabilities. The vulnerability, i.e. which assets are at risk and to what extent. We'd be more worried about nuclear power stations being at risk, for example, rather than a small solar farm. And yeah, vulnerability is it kind of gives us an idea of, or rather that's focusing on, were this event to occur, what would be the outcome and what would be the sort of negative damage expected at the site. And exposure is kind of which assets are exposed to the hazard itself. The research that we do is mostly focused on this ring, so characterizing the hazard, and it's the safety teams at the various nuclear power stations that can give a better a better overview of what the vulnerability and exposure is. And these three rings contribute to risk in this kind of way. Obviously, this is all very kind of simplified, but it's something like the hazard, which is your likelihood and the magnitude of that extreme hazard, times the exposure times the vulnerability, and we can sort of decouple the vulnerability into sensitivity to the hazard, minus the adaptive capacity. So this is kind of mitigation strategies. So a bit later on in the talk, I'll return to this hazard equation with respect specifically to space weather. So this is kind of the links that we have to universities in the natural hazards research team. So yeah, from the space weather point of view, there's probably a few people from these organizations in the call. So yeah, we're very much indebted to our academic partners for the research and the sort of safety that we can implement in our energy infrastructure. So one of the key perspectives in the energy industry, at least the nuclear energy industry, is that of nuclear regulators. So the ASN is the French nuclear authority, and the ONR, the Office for Nuclear Regulation, is the official regulator of the UK. So I guess I thought I'd just give a bit of an overview of what their guiding principles are and how we interpret those in order to stay kind of safe and protected from external hazards in particular. So the ONR have these what's called safety assessment principles, or SAPs. And these are incredibly long and incredibly dry documents, as you can expect. But I've picked out some of the key points for natural hazards. So they say for natural external hazards, the design basis event for an internal or external hazard should be derived to have a predictive frequency of exceedance that accords with the fault analysis principle. The fault analysis principle is that for external hazards, the design basis event should be derived conservatively to take account of data and model uncertainties. So the key word here is design basis event. And if we go to this box here, this is defined as a 1 in a 10,000 year event for external hazards. So that would include space weather, coastal flooding, earthquakes. So we need our nuclear infrastructure to be adequately protected against a 1 in 10,000 year external hazard event. And for internal hazards or man-made external hazards, then we need to be protected against 1 in 100,000 year event. So this includes aircraft crashes, fires, structural collapse, etc. And they are, the nuclear regulator is kind of fairly vague with their wording, or rather it's open to interpretation, let's say. So words like they should be derived conservatively, basically meaning that they shouldn't be, rather they should be robust to any uncertainties that we have in the data and the model. So if there's any uncertainties, then we should be sort of pushing the design basis to as far like to the top end of those uncertainties, just in case we are kind of wrong about the analysis due to uncertainties in the data or in the model. So to take this into account, we also need to be prepared for beyond design basis events. So this means events that are kind of even less frequent than these design basis events. The idea being that we want to make sure not just that we are prepared for these events, but also that there aren't these what's called cliff edge effects, whereby the risk would massively increase after you get past these to a particular severity. Like you don't want it to be acceptable at the risk to be acceptable at 1 in 1,000 year event, but then as soon as you get to 1 in 5,000, 1 in 10,000 year event, then it suddenly becomes much more dangerous or much more inadequately prepared for those events. So that's kind of the battle that we have in EDF to, or the incentive structure that we have in EDF to kind of correspond with the national safety structures. And specifically for space weather, so there's from the Nuclear Safety Technical Assessment Guide from the ONR, they say that it's acknowledged that the science of space weather is, as an external hazard is immature. So they're basically saying that they understand that compared to some of the meteorological hazards and other hazards, that the science of space weather is immature in the sense that there's kind of large bounds on the uncertainty, or large bounds on the values of the characterization of the risk. So we have like the confidence intervals that we have for the design basis events are really wide compared to, say, for example, coastal flooding or meteorological events, which have been studied for many, many years. And I guess space weather has this kind of complex entanglement of different physics and different effects that lead to these extreme events, and the amount of data that we have for space weather events is considerably lower than we do for meteorological and coastal flooding, for example, events. So they say that the strategy should take into account the level of uncertainty associated with the hazard characterization and its effect on components in order to ensure a proportionate and balanced response to the space weather hazard. So this makes it quite difficult for us because the uncertainty bounds are so wide on these extreme events for space weather. The ONR still would like us to build to those upper edge of the uncertainties, but if the uncertainty bounds are so wide, then it means that we have quite a hard task actually to build such secure and robust infrastructure with regards to the space weather hazard. So there's a few approaches that we could have to external hazard and natural hazard resilience. So one of them might be something like trial and error. So this would look something like wait for an extreme event to happen and then learn from it. And this could lead to hazard resilience. But the problem is, of course, that we don't know how extreme these extreme events can be. Obviously, we have past proxies, Carrington events, other large events, etc. But we really don't want to get to the point where we wait for the problem to arise and then learn from that as we go. And instead, we want to move towards this resilience by design principle. So this will be something like we just build such that even the most extreme events are just not a problem for the infrastructure, i.e. they can be robust against the most extreme events. So this would look something like, for coastal flooding, for example, it would look something like building a seawall that's sufficiently high that even the biggest kind of waves and sea level rise expected over the next 100 years, it would just be well below the level of the seawall. And for space weather, it might look something like enclosing the control room and electronics in enough concrete to mitigate the effects of solar energetic particles that reach ground level, and to be fully kind of resilient to any loss of mains power due to, for example, a GIC event. And in the middle of this, between these two extremes, we have resilience by operation, which is kind of this resilience principle that we want to avoid if possible. So we don't want to do any trial and error. We want to do as much resilience by design as possible. And if needed, then we can do some resilience by operation. And resilience by operation looks something like creating emergency procedures and creating operational procedures that would be put into practice during a hazard event. This is obviously a key part of safety, and needs to be part of the safety kind of mix. But it brings about or introduces some extra risks that resilience by design doesn't. So, for example, it brings in risks of kind of operational complexity, which can introduce things like human error. The control room booklets that they have to follow are in nuclear power stations are already huge tomes of books. So the more you add to that and the more operational complexity that you add, the more that you can introduce additional risks that are unforeseen. So it's this idea that we need to balance the risks when we're talking about resilience by operation. So to avoid that, we try and go for the resilience by design if possible. Okay, so space weather at EDF. These are some of the projects that we've done over a timeline over the last sort of 5 or 6 years. These two kind of circled projects I'll talk about in more details in a second, but we've studied the economic impact of severe space weather, looked into the vulnerability of transformers, effects of space weather on communications. We've looked into the duration of solar storms and how that is impacted by the severity, or how it correlates to the severity of the storm. But I will talk about two things, and there will be the characterization of the GIC estimates in the UK and France electricity networks, and the characterization of neutron particle flux at ground level based on due to severe space weather events. Okay, so yeah, I'll skip this slide, but I don't want to teach my grandma to suck eggs. Obviously, there's all of these ground level and space based risks. We're at EDF interested in kind of the GICs and the GLEs in particular. Okay, so GICs, this is kind of the chain of causation from the sun side all the way to kind of risk to EDF nuclear power station and other energy assets. So obviously this is kind of simplified, but we start with coronal mass ejections or kind of sun side events. If they're directed at Earth, we get geomagnetic storms in the Earth's magnetosphere. This can induce currents in the Earth's crust, currents flow along the power lines, overwhelms transformers, and then this can lead to loss of power to critical infrastructure. So you could say something like, well, why does an energy generating asset need power? Because it's creating power rather than needing power itself. But the idea is that if you were to try and shut down a nuclear power station, it takes some time to do so, to get it to a safe level. And if you lose key power to the mains electricity, then you need to go to backup power generators, and this can kind of introduce its own risks for the safe shutdown of the nuclear power station. So yeah, we're interested in characterizing the extreme GIC risk to the nuclear power stations. This is obviously a kind of history of the big geomagnetic storm events in history, the Carrington event and the 1989 event that caused blackout in Canada being two of the main ones that we have experienced. So what does it look like to characterize extreme GICs? Well, it looks something like estimating what the sort of 10,000 year return level of extreme GICs would be at different locations in the UK and France, but here I'll just talk about the UK. So to do that, as some of the other teams have talked about in the conference so far, we are basically using a GIC simulation procedure. We've done this with the help of the British Geological Survey in the past. And this involves a combination of kind of three main inputs. Obviously, we've got the network model, how the different transformers across the UK are connected. The ground conductivity model, how the conductivity varies with depth and in horizontal coordinates as well. For this, we used a kind of 1D thin sheet model developed by the British Geological Survey. And then we also need to input the geomagnetic field data. So for this, we analyzed several historical storms and the magnetic field data from those storms. But then to get those really extreme events, or analysis of those really extreme events, those 10,000 year events that we probably haven't seen because we haven't been analyzing geomagnetic field data for 10,000 years. Then what we do is scale those historical storms to the to what we expect the 10,000 year geomagnetic storms to be based on extreme value analysis of the magnetic field data. And then combining all these together, we get estimates of the GICs across the UK and across France. And that gives us an idea of the spatial distribution of the kind of GIC vulnerable parts of the network, and therefore which energy assets are vulnerable to that risk. So a quick view of some of the results. I won't go into this in too much detail, but I guess these are several of the locations of EDF nuclear power stations in the UK. And some key things to point out are the fact that some of the locations are much more susceptible than others. So for example, Sizewell here, we have just many times higher GIC expected in that 10,000 year storm compared to some of the other less susceptible locations. And another thing to point out is a comparison between different conductivity models. So we've done this, run this several times, once with the Eurisgic kind of block 1D compilation model, conductivity model across the whole of Europe, which is a great project for its scale across the whole of Europe, but kind of misses some of the fine-grained horizontal conductivity non-uniformity. So updating that to a conductivity model which has more of that non-uniformity embedded gives an update and hopefully improvement to the expected GICs. And it's quite a complex improvement, really. So some of the values would decrease by a significant amount, some increase, and yeah, it's really location specific. So some of the key results that we've had from our characterization of geomagnetically induced currents are that the 10,000-year currents are high enough to cause significant damage to transformers. This is, I guess, expected. This aligns with the results from other countries and other studies. There are certain nodes of the network that are many times more susceptible to high GICs than others. This is really key from an energy infrastructure perspective because it allows us to prioritize our sort of R&D, I guess, at those sites that are more susceptible. And it also means that we can give us a slightly different design basis depending on the site and how susceptible it is to the risk. But obviously there are many open questions. It's still somewhat, well, every year there's improvements being made to these models, and we're seeing kind of fairly significant changes in the estimates of the GICs. So while that happens, we are obviously getting better and better in estimates, but because they're changing every year, it sort of shows that there are kind of no agreed upon best practices or agreed upon best estimates for the design basis. So it's kind of an ongoing process. So some questions about how the improvements that we'd like to make to conductivity modeling would affect the GIC estimates in the UK and in France. And one of the problems that we've had in the UK is that it's been hard to find measurements of GICs to compare and validate the models against. So a key question really is how valid are these estimates compared to GIC measurements? So a second risk vector from space weather is ground level enhancements. So the causal chain from the sun to the effects at EDF are something like starting with solar flares and particle acceleration, leading to atmospheric cascades in the atmosphere. So you have ionization due to accelerated charged particles hitting the Earth's atmosphere. They cascade and cause interaction upon interaction upon interaction. And some of those particles, secondary particles, can reach the Earth's surface if the incoming particles have sufficient energy. And these can lead to local impacts known as single event effects. So in a particular component of an electronic device, you could have a bit flip, irreversible errors that can then lead to impact on a device. So could lead to erroneous results of an electronic system or complete failure. This is, of course, a problem for nuclear power stations because we just cannot afford to have any failures of electronic devices that are being used for safety critical shutdown procedures, for example. So the aim really is to characterize the risk from extreme GLEs. So we're aiming for something like an analysis of the 10,000-year GLE, so looking at what the peak flux would be at ground level of neutrons, what the peak fluence would be, or the total fluence would be over a full space weather event. So how do we do this? Well, we look at the data. About 1 GLE per year is recorded. The problem is that we only have data for the last, I don't know, 70 years or so, maybe a little bit more. This means that we're dealing with very few data points. And given that we see that the most extreme GLEs are just many times more intense than the average GLEs, it means that we have, well, we'd expect the distribution to be heavy-tailed. And this means that with the small amount of data, it's hard to get an idea of what the extremes are going to be over a really long time frame, like 10,000-year time frame. But that's kind of the best we can do, and we can supplement these data with paleoclimatological data from ice cores and tree rings, but this is again it's not exactly well understood how to interpret those data and how useful they are as proxies for the ground level flux that we're interested in. So I'll talk you through one of the studies that we've done, which was a data analysis study using neutron count data from a neutron monitor in Belgium. So this is the data set that we used. So we've got the peak flux of neutrons at ground level across through time for some key space weather events. And we did a statistical method known as extreme value analysis, which is where you are trying to predict what the extremes are going to be from the distribution in future. So we used what's known as a peaks over threshold approach. So this means that we fit, or we assign a threshold above which we say these values are the extreme values. And then we fit an extreme value distribution, in this case it was a generalized Pareto distribution, to those values, and then we can use those that fit distribution to predict what the even more extreme values would be over longer time periods. And we end up getting a plot that's something like this. So we have a return level, so what's the peak neutron flux expected over a given time period. So these are all the data points that passed this threshold for the peaks over threshold approach. And then this solid line is the fit distribution, which gives us a return level for a given return period. And obviously the further... Pardon?
2 minutes left.
Okay, thank you. Obviously the further away you get from the longer the return period you're trying to estimate, then the error bounds get huge, to the point where when you get to 10,000 years, which is what we're really trying to estimate because that's our design basis, they become kind of just fundamentally uncertain, because it's so far beyond what we've seen in the data. I'll just very quickly mention that we've also done some studies into how those extreme neutron flux levels at ground level would impact electrical components. So with some partners at the University of Surrey, we've studied a variety of generic electrical components, and finding that some electrical components are much more susceptible than others. So some key questions that we have about characterizing the risk from extreme GLEs are which estimates to use, really. So should we be using extreme value analysis, and how to incorporate these paleoclimatological data. Obviously, the study that I mentioned above was from data from Belgium, but of course that's going to give us only a flavor of what's going to happen in the UK or in France. It's not going to give us exactly what we're after. And yeah, some open questions about how these local single event effects propagate through to system level failures. That's a kind of key point here, that we're seeing some fairly high failure rates of electrical components, but we want to know whether they will propagate through to system level failures. So there's open questions there. I'll very quickly go back to the risk equation. So for space weather, the hazard part looks like characterizing extreme GICs and GLEs in the way that I've just talked about, aiming for this estimate of the 10,000 year event. The exposure looks something like considering which factors affect the hazard level for GICs and GLEs. So for each site, what's the latitude and location on the electricity network, and therefore how does that affect the expected extreme GICs and GLEs for that particular site. And then vulnerability, this looks something like, for space weather, what mitigation strategies can we use? So there's a few that I've listed here for both GLEs and GICs, and these are all, well, many of these are being used in nuclear power stations. So obviously nuclear power stations are full of concrete, so concrete shielding is obviously a big tick there. But we can use a variety of other things like computational redundancy within a system, so that we can minimize the effect of component level failure propagating through to system level failure. So I think I'll just leave the summary points up, and we'll take any questions that anyone has. I've been seeing there's in the chat several things that have been asked, but I haven't seen them yet. So, so thank you.
Great, thank you, Matt. I think we just have one quick question. If it's if John Morell wants to unmute.
Yep, okay, if you can hear me. Quick question was, you wrote off the loss of GPS or satellites in general in the beginning of the presentation, but I thought that the GPS system is used for precision timing in various places. I know the cell phone network may go down if GPS fails for long enough, and I believe certain of the railway signalling systems will, but that's another story, another place. I wonder what the impact of that would be on your power stations.
Yeah, so yeah, that's a good point. I didn't mean to completely say that it wasn't important. So yeah, it's definitely a key consideration. So we have, well, my predecessor looked into this in quite a lot of detail in a study into the effects on communications. The main interest from the nuclear energy point of view is kind of how we can get a nuclear power station in the event of a very severe event, a severe space weather event, how we can get a nuclear power station to safely go from running to shut down without any problems. The problems come in when you can't easily make that step from safe running to, oh, there's a big event that's a problem, to shut down. And it would take an extraordinarily big event for this to happen.
That's what happened 10 years ago, of course, almost to the day.
Yeah, of course. Yeah, absolutely. Not to do with space weather, of course, but
No.
But yeah, this is the key. This is why there's this kind of push for natural hazard R&D in the nuclear industry. Yeah, I guess the point is that the systems in place that are there to take us from operation to shutdown do not rely on human input. They can involve human input and can be overridden and all of that, but by default they do not rely on human input, and they can be kind of quickly shut down without that. So phone kind of reception going wouldn't be a big issue. There's also other, I can't remember what it is, but there's other communication technology that's used for an event where mobile technology would go down. I guess the point is that the system would be secure even if comms went down in that particular event.
Yes, no, I think comms was only one area. Mike Catgood has actually commented about the grid itself. He doesn't believe that the grid itself is susceptible to the loss of GPS or for timing, but I don't know. It's not an area I'm an expert in, I must say.
Yeah, regarding the GPS timing, I'm also, I'm not exactly sure what the risk for that is. I think it was covered in some of the previous work, especially the one that was on kind of economic impacts of the of space weather. That included analysis of GPS, but I can't remember off the top of my head what the details of that were.
Thank you. Okay,
thanks for the question. If there are any more questions, I'm sure we'll be able to catch up in the poster session or catch up by email or whatever. But thanks, Matt, very much. I'm going to hand over now to Gemma, and hopefully go on to the next session. Cheers.
Okay. Oh, hang on. Can I just check now, which screen are you seeing of mine? Is it
We can see the presentation.
Yeah.
Is it in presentation mode?
No.
Okay. Anyway,
It's a
we'll just
slide
carry
show.
on and hopefully this will make sense. So the poster session is going to happen in Gathertown, and I've just put the links in the chat, but you should also be able to find them in your email and that the Zoom links are in as well. We have 2 poster rooms and then an extra overflow room just in case there's not enough space in those first 2 rooms, but I think there should be. So for anyone who's not familiar with Gathertown, they look something like this, and you have a little avatar that you can move around with the arrow buttons on your keyboard. And to look at a poster, if you move to the poster and then press X, it'll bring the poster up. And on the right hand side, there'll be 3 very faint buttons that are actually quite hard to see that allow you to zoom in and out so you can actually see the poster in more detail. There can be issues between getting your video to work in Gathertown if you're still connected to the Zoom meeting, but I think as long as the video is turned off in one of them, it should work. But if all else fails, you can leave the Zoom meeting, connect to Gathertown, and then the Zoom meeting will still be there when you come back. So if we just go ahead and we're going to give all the poster presenters 2 minutes, and it will have to be quite 2 minutes because we're running a little bit tight on time, to just talk about their posters. So I will show the posters on the screen. And just to check again, so is this still showing this in PowerPoint, or is this showing you the actual presenter view? Can someone just check?
It has the PowerPoint around.
Okay, I'm just going to change that so you get the full size. Apologies. For some reason it's not. There we go. Right, so poster presenters, if you can just unmute yourselves, and I'll give you a warning when there's 30 seconds left. So our first poster is from John Coxon. So take it away, John. Ooh, you are muted.
Brilliant. Hello, everyone. So this is a poster on the distribution of Birkeland currents. Birkeland currents are the current system that links phenomena at the magnetopause to the ionosphere. And as such, they're a huge part of understanding how the current systems in the ionosphere are driven by external stimulus, such as from the solar wind. And so I present the key points of 2 studies in this paper, one dealing with temporal distributions of Birkeland currents, so how quickly it takes currents in different regions to react to IMF stimulus, and then the other looking at spatial distributions, so looking at how these currents are distributed in each coordinate, and then looking at what that implies for where we think the most extreme Birkeland currents are likely to flow, which is down there in the bottom right hand corner. So if you'd like to find out more, either scan the QR codes to go to look at the temporal distribution paper, or come to the poster and chat with me to learn more about the spatial distributions and probabilities. Thank you very much.
Thank you. Excellent, John. So we'll now move on to, I think Xiangcheng Dong is going to talk you through this poster.
Can you hear me?
Yes, go ahead.
Hello. This poster is about the intense ground DT variation and the scaled field line current in the ionosphere and the magnetosphere, driven by near-Earth BBFs. We investigated the characteristic and response of magnetosphere, ionosphere, and ground system during a storm by using a multi-point approach, which combines the space measurements and the ground magnetic observations. And the multi-BBFs events are detected in the inner magnetosphere, and the magnetic footprints of magnetospheric and ionospheric satellites map to the same region near the magnetometer ground stations. And our results provide direct evidence that a wide range of intense dV of dt or dH of dt variations are associated with large-scale substorm current system driven by multiple BBFs. Thank you.
Thank you very much. So if we now move on to Juliane.
Hi everyone. I made a poster about the differential magnetometer data that we collected in SWIX, and it's one of the data outputs that we have, and most of it is now available within the National Geoscience Database. And I want to encourage you to use it because it's meant to be used as a proxy for GIC and indeed also for electric field data, because we don't have so many observation sites in the UK, and this line GIC data that we collected can be used at this. And the poster is just a rough summary of things I've shown in other talks or posters before, but just to say quickly, to describe the method and describe the data and tell you what we are doing with it at the BGS, where we are trying to increase the accuracy of our GIC network model. And there's also some curious things in the data where we can see the development of GICs across the GB network, just because our data coverage is better. Yeah, just meet me in poster room 1.
Excellent, thank you very much. So our last poster from poster 1 is from Anna.
Yes, hello. So in the Ibergcast project is a project submitted to the Spanish agency by 3 groups of research groups of Spain. 2 of these groups, the University of Barcelona and the Ebro Observatory, are already working in a project. And here we present some of the main highlights. First is the construction of the lithosphere geoelectrical model, which is based on the inversion of magnetotelluric data and the inclusion of geodynamic and other geophysical constraints. The other part is that we have characterized the GIC sources. We are working on the measurements of the GIC using differential magnetometry. And we have modeled the 400 kilovolts and the 220 volt network. In this new proposal, we have included a group of theoretical physics of the University of Valencia, which are going to deal with the deep learning to predict the geomagnetic variations that lead to the GICs from the study of satellite data of the solar wind parameters. More specifically, in our sub-project, the main goals will be to improve this lithospheric resistivity model, including data from the Canary and the Balearic Islands and from Portugal. We will construct hazard maps of the electric field, and we'll explore the use and the measurement of new transfer functions between the GICs and the magnetic field. So I will explain more things in the poster session. Thank you.
Okay, thank you very much. Okay, so moving on to poster room 2, where we have 3 more posters. So our first one is Cameron. So Cameron, would you like to take it away?
Hello, can you hear me?
Yes.
Right. Hello, everyone. I'm Cameron Patterson. I'm a first-year PhD student based in Lancaster University. My project involves investigating the impacts of space weather on the UK railway network. For the time being, at least, I'm focusing on the impacts on railway track circuits, which are an integral component of the network signalling system. These track circuits detect the presence of a train when the wheels and axle of a locomotive cause a short circuit in the system, which can change the current running through the sensor. So you can gather how geomagnetically induced currents could cause an imbalance in this system. To determine the extent at which these track segments are affected, I first need to know the trackside geoelectric field, which can be obtained using magnetic field variations and a conductivity model. But unfortunately, most railways are distant from magnetometer stations, so an interpolation method is needed to sort of make up for this sparse data. So in my poster, I mainly discuss the implementation of the spherical element current system method, which generates equivalent ionospheric currents and then uses those currents to interpolate the magnetic field at a desired point. lots more work to do. I've only just begun to scratch the surface of this new project, but I'm looking forward to discussing my work with you after lunch. Thank you.
Excellent, thank you. And so we'll move on to Neil.
Yeah, hi. My post is on looking at the statistics of very large fluctuations in the magnetic field, so dB by dt. We've used a huge database of supermag data, which is sort of 1 minute cadence data, and we're looking at sort of changes over these sort of timescales, and we're looking at the sort of high percentile, 99.97 percentile, which might be exceeded every a few times a year, but also using extreme value theory and sort of extrapolating that to the sort of 1 in 100 year return levels for dB by dt, and showing how these events can depend on the local time and also where you are in latitude. And then for 3 stations in the UK, we've extended the data set using some 1 second cadence data. So we can extend these distributions of the return levels as a function of the period of the fluctuation right up to 1 Hertz. And we can determine the geoelectric field extremes as well. So yeah, please come to see me in room 2, I believe.
Yep.
Yeah.
Okay, thanks, Neil. Then our final poster is from Rob Shaw.
Hi everyone, I'm a postdoc at British Antarctic Survey. So this poster is describing a number of studies actually into modeling the sources and behavior of the geomagnetic variation at the poles and mid-latitudes in the Northern Hemisphere. These span the SWIGS project and are now continuing into the Swimmer SAGE project. So in the first of these studies, we developed a technique to isolate the ionospheric equivalent currents from a large set of ground-based geomagnetic variations. And then we show how these individually relate to their respective driving factors from the solar wind or from substorms. These are the component parts of a meteorological reanalysis of space weather impacts at ground level. So this tells us where you expect space weather to be, how big the amplitude is, and why it occurs. In the subsequent study, we actually do the opposite. So we start with a solar wind driver, and then we use a new technique that we developed to isolate the response function, so I should call it, of that driver within the total set of ground-based data. So this again tells us where we expect space weather to occur, but it also tells us when we expect it to occur and how long we expect the effects to last. So this new technique allows us to investigate not only the physics of how the solar wind driver affects the Earth, but also paves the way to a forecast model of the directly driven geomagnetic variations for the UK, which we're currently undergoing development for the Swimmer SAGE project. So if any of that sounds interesting to you, feel free to pop onto my poster. Thanks.
Thanks a lot. So thanks to all the poster presenters. We've now got officially 15 minutes for lunch, but the poster rooms are already open if you want to go and have a look at any of the posters straight away. And we will come back to the Zoom, I think at 2 p.m. sharp, because we're just about on time. And we'll do an announcement in the chat in Gathertown to remind you that it's time to come back. But for now, I will leave you to go and enjoy your lunch. And if you have any problems connecting, then let us know in the chat or the Q&A here. Okay, thank you very much.
It's just turned 2 o'clock. If I have definitely not muted myself. Welcome back. First of all, say thank you to all the speakers, poster presenters, and of course my co-organizers for organizing and chairing the morning session. I thought it was really good. And certainly I'll be one. A few people have been asking me about whether this is being recorded and will be available later. I know it's being recorded. The details of how it will be made available, unless someone can correct me, I think will come from the RAS, but we will keep an eye on that. And I myself will need to refer to it at some point. There's been so much happening. Okay, so we'll move on to, we've got 3 speakers this afternoon, and we have a short period at the end where we may have a slight discussion. It slightly depends on the timing of the whole thing. We do have to finish promptly, I believe, at 3:30. So let's just judge that as we go. For the speakers this afternoon, Peter Gallagher, Jonathan Eastwood, and Chigomezyo Ngwira, 2 of you have a 20-minute talk, and I'll let you know when you've got 3 minutes left. For Chigo, I'll give him a 4 to 5 minute warning because he is closing the afternoon's presentations with the keynote. And with that, I will stop sharing my screen and I'll invite Peter Gallagher from the Dublin Institute of Advanced Studies to talk to us about solar and geomagnetic monitoring and modelling in Ireland. So Peter, you're welcome to share your screen now.
Thanks, Alan. Can you see that okay?
Currently, I'm seeing you.
Share. How's that?
That's it. Thank you. Yes.
That's a vast improvement.
Thank you.
Okay. Thank you very much. All right. Well, thank you very much for the opportunity to come and talk a little bit about some of the work that we've been doing at the Dublin Institute for Advanced Studies with other collaborators. We're primarily interested in understanding the impacts of solar activity, solar flares, CMEs, SEPs, and so on the geomagnetic field and on the ionosphere. But in this project, we have a particular focus on the environment of Ireland and also in the infrastructure in Ireland as well. So in this talk, I'll give you an overview of some of that work. Very much is an overview talk, and there's plenty of references in there if you want to dig a little bit deeper. So our research focuses on really the full complement of observations from the sun, solar flares, and right through to eruptions, coronal mass ejections, and their associated solar radio bursts. But we have also developed instruments within Ireland that look at the ionosphere and also at the geomagnetic field. And on using those pieces of information, then we've developed models that are based on BGS models, in fact, to model variability in the geomagnetic field in Ireland, but also GICs, and to try and understand levels of GICs within Ireland, and also worst case scenarios as well. The instrumentation that we have developed over the past decade really include everything from solar radio observations and facilities like you can see there on the right hand side. This is the LOFAR radio telescope. But we also run the website solarmonitor.org that's constantly monitoring what's going on and near the sun in terms of everything from active region evolution to solar flares to coronal holes. But today I'll focus primarily on the setup of these and some results, and actually some new results from both of these instruments, because I think they're most interesting to those at this meeting today. So I'll talk about ionospheric monitoring and geomagnetic modeling, or monitoring, should I say, well, monitoring and modeling actually for the geomagnetic work. So what are VLF? Probably most of you are familiar. You have a transmitter that emits VLF waves at typically 3 to 30 kilohertz, and they bounce off different layers within the ionosphere. depending on whether or not it's daytime or nighttime. During daytime, we have a D region formed primarily due to Lyman alpha ionization that causes this D region to appear, and that results in a higher electron density, which you can see here on the right-hand side here, and then we get this higher electron density formed that allows a bounce at lower altitudes, getting down to less than 100 kilometers. But if you have a receiver at some distance from the transmitter, you can then monitor the D region, and that is very much modulated by solar activity. So even the smallest of flares, be they what are called C-class, some of the smallest C-class flares are quite visible in these kinds of data, right up until X-class flares, where it can be quite appreciable. And of course, shortwave communications and so on can be affected. So this gives us a way of monitoring what's going on in the ionosphere, and particularly the D region, which is difficult to look at otherwise. You either need to fly through it or use VLF to really get a sense for what's going on in the D region. Very good example of D region ionization and disturbance being seen was in September of 2017, when there was a number of X-class flares, which are shown here on the right-hand side, this X9 and this X8 flare. But at the time, the sun was just over Western Europe, Western Africa here, but this day side of the ionosphere was illuminated by this, and of course this caused numerous radio blackouts, communication problems, air traffic control problems, and so on. Notably, this was during the period when emergency services were most interested in responding to issues around hurricanes Irma and Jose that were happening in the United States. So, for communications, understanding the ionosphere and the D region in particular are of importance. Now, the instrumentation required to do this isn't complex. These are a couple of magnetic loop antennas that we have erected. Well, these are upgraded versions in the past 6 months. Interesting during COVID times, but they are now up and running. We have one in Birkeland, which is in the center of Ireland, shown on the left-hand side there. And this is about 2.5 meters across, and about 10 windings. Over here is at Dunsink Observatory. Again, actually this is about 3 meters across, and again about 10 windings. What they allow you to do, though, is to tune into a variety of different transmission stations. So here's say Burr connecting to NAA, which is a transmitter in Maine in the United States, and we can monitor the ionosphere as those VLF waves propagate across the Atlantic Ocean. Likewise, if we want to look to the east, there are a number of other transmitters that we can look at from southeastern Europe and out onto Moscow, to give us a view of what's happening to the ionosphere both to the west and to the east of us. So these are the kind of data that we receive from these transmitters. Here's looking west to the United States. This is nighttime up here, and then this is the day-night terminator. Then we have the daytime, and this is local noon, and so on. But then if we want to look over to the east, this is a data dropout, by the way. The transmitter was down for maintenance, I'm guessing. But it shows the same general shape, nighttime and daytime, with this characteristic shape in here. Now, the ionosphere and the level of ionization in the ionosphere is very sensitive to Lyman alpha, but also to ultraviolet, well, extreme ultraviolet and X-ray. And so within these curves, you can sometimes see flares occurring. So effectively, the ionosphere becomes a large X-ray detector for us. And here's an example from just last week, and this is from the March the 9th. This is the flare here seen in GOES X-rays. So it's what's called a C-class flare. So that's a small enough flare. In a few years' time, we will not be getting excited about it. At the moment, we are quite excited about it, but it just shows you this is a signal coming in from Germany, but detected at Dunsink, and you can see that there has been you know, an ionospheric disturbance that happened at the time of the GOES flare. So it gives us a clear insight into what's happening in the D region and how that's related both temporally and spatially to the X-ray activity on the sun. Now, these solar flares also have variability in them on timescales of minutes. These are a series of observations from Laura Hayes, published in JGR in 2018. And what it shows you on the top right is the GOES variability. So a number of flares going off and pulsations really within the flare. But also you can see the VLF signal responding very sensitively to this. So basically telling you about the ionosphere and the ionospheric ionization being very dependent on the flux from X-rays. It just so happened that this flare occurred when the sun was over the Atlantic, and then we can look at the phase and amplitude of the signal between NAA and Burr to work out properties of the ionosphere. Now, there are simple models that you can use, and this is a very straightforward model here. So say if we have our transmitter and our receiver, then we can work out the height of the ionosphere from the data of the D region, should I say, and also how quickly it falls off. You know, is it a step function fall off, or is it a smooth fall off? And that's what that beta parameter tells you about, and this is the electron density model that we can use. But what you can do with that, though, is then make estimates of the height of the D region, so here's the height of the D region as well, and you can see during these pulsations the D region descends from 74 to 64 by 10 kilometers, and also you can see this roll off in this beta parameter. You can also look at the electron density as well and try and work out electron density profiles. So what these simple VLF with quite a straightforward model called the LWPC model can do is give you an understanding of the ionosphere, the D region of the ionosphere, its height, the degree of ionization in there, and the electron density within that. And that can be important then when you're going on to do some modeling of what's happening at the ground, if you want to have some understanding of what's going on above you. And that leads on directly really to the MAGI network of magnetometers that we've been developing. This is called the Magnetometer Network of Ireland. Over the past, nearly 6-7 years, we've deployed a number of magnetometers. Met Éireann, our Met service, has been running one for many, many years, over a century really, at Valentia Observatory down in the southwest coast. We also installed a LEMI magnetometer at Burr in the Midlands, and also another one in Armagh, and have been running them as part of a network. Now, we have had problems during COVID with maintenance, which has been very difficult, so we are having problems with them at the moment, which is typical. But also we have at Dunsink Observatory purchased a census magnetometer that actually BGS have also been using, and we now have a test installation taking data. The data are not live as yet, but we're hoping that in the next couple of months, and certainly over the summer, that we'll have a fourth station live delivering data. This one is intermagnet quality, I should say, and the other ones are not currently intermagnet, but we do have ambition for Burr and Armagh to be upgraded to intermagnet quality installations. We take those data in near real time and then produce data that's available on the MAGI website. On the top left, you have BX, BY, BZ over 3 days in January 2021. And then over here, we have DH and DHDT as well, just showing on a relatively quiet day. Sean Blake, during his PhD about 5 years ago now, used these to then calculate the local K index for each of our sites. So this is over January the 30th, the 31st and the 1st of February 2021, just showing a quiet period where there was not a lot going on. We do have a service, fledgling service on the website where you can sign up and get an alert. And then this is, you know, what you saw on the 1st, 2nd, and 3rd of March of recently. So there was up to a K6 seen, and then once you go above a certain threshold, you can get an email from us and a link to those data as well if you're interested. So with the magnetometer data, then we're able to do more detailed studies of both B fields and E fields across the island, and then try and work out GIC levels through the grid, through the power grid. This is all based on, or some of it is based on the modeling work of Joan Campagna, who came up with this SWEMD, the Space Weather Electromagnetic Database for Ireland. But on top of having these permanent sites, he also took many different time series measurements of both E and B fields at multiple other sites, corrected the time series for steps and noise and so on, but then developed tensor relationships between the E and B fields at each site and between other sites as well. As part of this also, then this leads on to being able to get a 3D model of the conductivity within the lithosphere down to about 1.3 kilometers, down to about 1,300 kilometers, 1.3 megameters into the lithosphere, and then plus or minus about 1,500 kilometers as well. And with that, then the database also includes several case studies where, knowing the conductivity maps, knowing the E and B field relationships, we can then look at time variability in E and B fields at all of these sites. So this is work that's now continued on by John Malone Lee, who's doing his PhD working on this. And this just shows using this interpolation scheme and then working out both the magnitude and the direction of the magnetic field at all of these sites that have been surveyed in terms of their MT. So we can use these 3 permanent sites and the tensor relationships with interpolation to then work out what these are. And if you have then time series for each one of these in terms of the B field, you can then generate time series for all of these other sites where you know the tensor relationships quite well on the ground conductivity. And so this is initial results coming out from this work. This shows real time, well, it hopefully will be real time in time, but it's a particular period, 8th of the 9th, 2017, just looking at both the strength and the magnitude of the E field. And of course, you know, knowing the vector and its magnitude is important for then correlating it with the conductors that are in the power grid and working out what kind of levels of GIC are going to be in them. Associated with all this, this then allows us to make things make maps, which we call risk maps, and looking at magnetic fields, variability in the magnetic field and the electric field, and how bad they can be from a variety of different scenarios. So it gives us a better handle on where on the island there are the more likely areas for high variations in any of these quantities, and hence in GICs. So that brings us really onto the GIC modeling, and of course this is quite straightforward to many of you, but with these surveys and more comprehensive understanding of the ground conductivity, we can then model the GICs, and this is work we've done with Alan and Kieran and others within BGS. But here's a movie taken from a paper from 2016 in Space Weather by Sean Blake, but just shows modeling of the 2015 March 17th event, appropriate considering that next week is one of its anniversaries. But what it's doing here is giving you the horizontal electric field and then looking at currents flowing through the power system. Now, in this case here, we were only looking at the higher voltages. So I think that was 400 kV and the 275 kV were only included in this, in both the Republic of Ireland and...
So you've got 3 minutes left.
Okay, very good. and the Republic, and it can give you an idea of where the largest currents are likely to occur. So you can see up here in Belfast Lough, and then down here at the Shannon Estuary. Of course, these are our largest east-west conductors that are bringing power from power generation down here right up to Dublin, where the most consumption is done. And that's where all the data centers are as well. So as part of this work, we extended this work to include right down to 110 kilovolts to see what the effects this would have on the distribution of current through the system. And what's interesting, you can hit this then with a 1 volt per kilometer a northern directed field or eastern directed field, and look at how the GIC level is. And this is seeing maybe 100 amps flowing through this area here, so potential risk. And what was also interesting to do is to then look at the effects of adding in this 110 kilovolt network. And what it does is, what you're seeing here is it's actually leading to the vast majority, certainly in the north-south, it's allowing current flow throughout the network and dissipating. And this is known, Tort have done work on this, and GROW as well has done work on this in the past number of years. So I guess in the future, just to wrap up, we're still working on, and I'm quite embarrassed to say that I showed the slide 2 years ago, and there was only a few changes in it, but we'll get there. The magnetic field work, we're looking to upgrade Bur and Armagh, so there's some just digging and work to be done there, but we'd like to do some event detection and forecasting. With the geoelectric field work, really we've made a lot of progress in the last 3 years, and should be soon posting those real-time electric field maps on maggie.ie. And then also the ionospheric work, we'd like to get more sensitivity in there and more transmitters as well to give us more comprehensive view of what's going on in the ionosphere. So with that, I shall stop and leave some of the contributors to this work, who are many and varied, and happy to take any questions.
Thanks, Peter. That was great and very comprehensive. There's a lot of work being done there.
Probably too fast, but anyway.
You're fine, you're fine. There are a couple of questions on the chat from Ilko Doornbos, John Jarnecki, and Mike Hapgood. I'll take the first one. I think we've probably only got time to ask one, and perhaps, Peter, you could maybe try and answer the others in the chat function.
Yes, will do.
The first question came from Ilko Doornbos. He's interested to hear about how you made the conductivity model using the magnetometer time series over a large number of locations. And I think specifically, what is the approximate duration of the time series that is needed to create a good conductivity model?
Yeah, we actually went and did the surveys and left sites in place for several weeks is the way we did it. And in fact, some of the sites were several months as well by the time we got back around to them. So it's many weeks is the timescale that we were using for that. And I missed the first part of that question.
I think that was just his introductory remarks, that he's interested to hear about how you made the conductivity model.
Okay.
Sure.
Yeah, there's a paper by Juliane Campagna et al. That you could have a look at in Space Weather that goes through that in great detail. Yeah,
I remember it. And it's a good paper. Okay, thanks, Peter. That was great. Please do, if you want to follow up some questions on the chat, that would be great. But we probably ought to move on and
stop sharing.
Stop sharing screens. And I'll ask our next speaker, Jonathan Eastwood from Imperial College London, to talk to us about the translation of the Gorgon magnetospheric model for operational space weather forecasting in the context of the Swimmer SAGE project. And I'm sure Jonathan will explain all these acronyms. Okay, Jonathan, over to you.
Hi, Alan. Hi, everybody. It's great to be here. Thank you very much for the opportunity to speak. I'm gonna share my screen. Alan, you could tell me if it's coming or not, I guess.
Yep, that's it. We can see it now.
Okay, brilliant. Right, so yeah, my talk today is about some of the work we're doing as part of Swimmer SAGE. And as Alan said, there are a lot of acronyms, and also I think there's a lot of people here, especially in the students, who probably aren't aware of everything that's going on. And so today I wanted to talk a bit about the Swimmer project, where SAGE sits within that, and then what Imperial College is doing at the moment inside that as part of an overall effort to really try and improve our ability collectively to understand, mitigate the risks of space weather as in applied to ground effects, essentially. So I'm speaking on behalf of an increasing number of people at Imperial working on developing these simulations, and also as part of SAGE. And also I do want to acknowledge SWIGS as well, because it's a lot of very important science. I'm going to talk about that as well. And so our colleagues there have had a big role to play. So Swimmer is a 4-year project which is funded by the Strategic Priorities Fund, and that's part of UK Research and Innovation. It is not strictly inside the research councils, but it's administered through NERC and through STFC. And so as part of this, there are 5 consortia who are looking at different aspects of space weather impacts. And the goal of each of these consortia is to make a step change in the ability of the UK to respond to severe space weather. And that's primarily through providing new tools to the Met Office. And so to be deployed through the Met Office route. And so the one I'm going to talk about is SAGE, which is in red here, and this is for ground effects forecasts. And the key aim of SAGE, and SAGE stands for Swimmer Activities in Ground Effects, is to essentially for the first time provide predictions of the ground electric field in the UK, to model how this will affect various infrastructure, so power, pipeline, and rail, as an example. And most importantly, perhaps, is to make this information available to stakeholders. What we want, or the aim, is to have information which is actionable, which can be used beyond the science community. And so overall, help society in that way. And as I guess people know, the PI is Alan, who is here, and these are the other people, groups involved. So what does that actually mean? Well, what we want to do is provide accurate nowcast and forecast. And if you want to know the ground electric field, then you need to know the ground geomagnetic field as well. And so this then means coupling together different types of models. And so we're looking at taking, essentially starting with data from L1, solar wind, or at least the upstream data, communicating that through magnetospheric models to the ground, and then to models of transmission networks to make the forecasts. Sort of more pictorially, of course, this is broken up into work packages. And so I can never remember with Zoom if my cursor is appearing on the screen or not. Can you see me moving it, Alan?
Yes.
Okay, sorry. We have to use so many different technologies, and they're all slightly different. So the first bit is forecasting. I'm going to start in the middle here, and this is using different models, which I'm going to talk about in a little bit more detail. So part of it is what we're doing at Imperial. Other parts are done not using MHD in different models. So Rob Shaw's poster, please have a look at that, because that's talking about this, the spider model, and also models available at the Met Office, taking extra new data from the UK on the ground. So Juliane Hübert, whose poster is here as well, talks to that, putting it through better models, and then making forecasts, working out the impact on infrastructure, providing visualizations, and also for context, using new methods with machine learning. And this is Andy Smith at MSSL in particular, who's taking the lead on this, to really try and build an improved system for us all. So I'm going to really only talk about the ones in the red boxes. because these are what Imperial College is contributing. And this is in task 2.1, providing MHD simulations using the Gorgon code, and then working to build, couple, validate, and verify something that can ultimately be used operationally. So having given all that context, I'm now going to spend the next few minutes talking about what we are doing at the moment in terms of magnetospheric modeling. We have an ongoing program which began by leveraging expertise in plasma physics in the Department of Physics. So between myself and Professor Jerry Chittenden, who's in plasma physics, we have been developing this global magnetospheric model for a number of years now. And it's played, we've had the benefit of being part of a number of different consortia, which has helped to translate this towards in its use, in particular SWIGS, of course, and RADSAT as well, and now also using it in Swimmer. And what you can see on the left-hand side is a simulation by Joe Eggington, who's my PhD student. And this is interaction of a shock arriving at the magnetosphere and compressing it. What we've learned, or what Joe is showing here, and what we've learned is that actually looking at the pressure is one of the nicest ways to get a really good visualization of the structure of the magnetosphere. And below, we've got some ionospheric maps which show variations in the field line currents and in the cross-polar cap potential. And so you can see the shock arriving. As I said, this started in laboratory plasmas, and I just got a few slides because they're really pretty, essentially. But this is a picture of the plasma experiment in the basement of the physics building at Imperial. This is called Magpie. It's a Z pinch, and basically you blow a megaamp of current through a very, very tiny wire and turn it into a plasma. This allows you to do all sorts of interesting experiments. They do a lot of astrophysical plasma experiments, and so this makes contact with some of the things that we're doing here. In particular, they're doing experiments in laboratory plasma reconnection, laboratory shocks, and so on and so forth. And a lot of people ask me, why is it called Gorgon? And the answer is that actually it doesn't stand for anything. It's because when they were doing these simulations of Z-pinch claps, produces these tendrils of material. And so it was very reminiscent of the Gorgon. And so that's how it ended up with its name. And that's what we use now. Now, to talk a bit more about the details, again, I've shown this in other contexts. I'm not really going to go through all the details. I think the main point I want to make here is that every global MHD simulation attacks the problem in a different way. Even though you want to essentially solve the same physics, there are many different ways that you can cut the equations up and solve them. And so that's important because it gives you forecast diversity. If everybody uses the same model with the same solution to the physics, they will get the same answer. You have different models approaching things in slightly different ways, then that starts to give you better insight into what the key things are that's controlling what's going on. In our case, for example, we don't actually solve for the magnetic field B, we actually solve for the vector potential A. And that automatically means that div B is 0 to machine precision. And so that means you don't have to worry about so-called divergence cleaning, but you pay a price that I'm not really going to get into here, but it's to do with how you deal with the grid and everything else. So there's different ways to do it, and this is another way that it's used. In terms of how we construct the simulation domain for the solar wind magnetosphere problem, we follow a very well-trodden path, which is essentially to couple the magnetospheric domain to a thin shell ionosphere. We couple it through field line currents. And actually, notwithstanding what I said on the previous slide, this is a pretty standard way to couple these two things together. And what we're doing is very similar to other groups and other codes. Now, in terms of what we are working on at the moment, I wanted to highlight one result which was published last year by Joe, which was looking about how the dipole tilt affects the location of reconnection X line on the day side, and also the overall configuration of the magnetosphere. And this developed a number of tools that we're going to use for the SAGE project. We're also translating results from SWIGS. And so here we have some very, very important basic science questions about variability in the global magnetic field. This actually relates to what we heard this morning about from EDF Energy and the talk that we heard about long timescale impacts. If you're worried about events that have a return time of 1,000 years, then you start to have to worry about how much does the Earth's field change on 1,000 years. And so working with colleagues at Leeds, this year we're still in the final part of the SWIGS program. We're really hoping to understand this a lot better by modeling with different dipole field strengths consistent with what we know has happened historically. We're also doing extreme events, for example, the 2017 storm, which will also be used, I think, as a benchmark in the SAGE project. So moving into what we're going to be doing, there's a number of different ways that you can take data from an MHD simulation and use it to calculate or predict the ground magnetic field perturbation. On the one hand, one method which is in the literature is called calc delta B, and this is a Biot-Savart integration. So basically you take the current densities over the whole magnetospheric domain and over the ionosphere and everywhere else, and then you calculate the magnetic field perturbation at a point based on all of those current elements. And this, for example, is used up in the space weather modeling framework approach. But as you will know, Biot-Savart is a magnetostatic approach. And so that leads immediately to questions about how do you deal with time variability. On the other hand, there are methods, for example, the complex image method, which is much more based on ionospheric current systems. And so there you take lots of elements of the ionospheric currents, and you can then integrate or calculate the ground magnetic perturbation in a different way. Again, how do you deal with other regions exactly? And so there's different ways of doing it to ultimately, and this is what we want to know, and this is from Kieran Beggan, which is actually the measured magnetic field perturbations for the 2017 storm seen over the UK. So how do we get to predicting this? I can see a lot of flashing of questions, but I guess we wait to the, because I can't see them. I have to address anything at the end. So what we want to do actually is to make a resilient methodology. And what we're aiming to implement in the course of SAGE is a cross-strapped system which will allow us to use everything at our disposal. So both the code that we're developing, Gorgon, SWMF, which the Met Office are looking to implement, and of course one could add other codes as well on that layer. And we could have different ways of calculating the ground magnetic field. And we could actually implement all of them. And it may not be the case that there is one perfect method which a forecaster should use to address this problem. My feeling at the moment actually is that the forecaster is going to want a variety of model outputs and then be able to use some human judgment to decide what to take from each of those to reach an actual forecast. And so this is the philosophy that we have in order to pull all this together in the SAGE project. So that's one part of the work. The other part is optimizing for forecasting in the UK. And essentially, there are many things that you can play with within the global simulation, each of which is tensioned against the other and is tensioned against how fast it will calculate and other things. And what we want to do is to address the very specific issue of improving our forecast here in the UK and looking at how best we should set up the model so that we get the best that we can. And so this will be another part of the work that we are going to be doing. And so now putting that back into the context of what SAGE hopes to create is that this is one of a number of different models. So I have briefly mentioned them. I can talk more at the end as well. The first thing is to get them all operating independently. We'll be moving to working in the Met Office IT environment. And so we're going to be, we have actually now got Gorgon running on very initial stages on the Met Office facilities. And so over the next year or so, we're going to be looking at really getting that running properly and then building with all of our team partners a coupled model going all the way through. And so we'll be running on Monsoon in order to do this. So that brings me to the last slide that I have today. I hope that it hasn't been too quick, and I know there's a lot of acronyms. I've talked a bit about SAGE and what the overall goal of that is, and I think it's important to say it's a translation of the knowledge that's been gained to a very much more directed and kind of operational goal. But already in the discussions about how this might work, it's already prompting new idea questions for research to go back and study other things to work out, you know, as new problems are confronted. And so I think there's going to be a very symbiotic relationship. I've very briefly talked about what we're doing at Imperial. And, you know, overall, what I am hoping in the next few years is to basically make Gorgon as available as possible to the whole community, so that it can be used widely. And this is really part of our ongoing program. So that brings me to the end. So I will stop there and just say thank you very much, and hope there's some questions. Thank you.
Thanks, Jonathan, but that was very interesting. And indeed, I mean, I'm obviously going to echo what you said about starting to transition of it based on physics understanding, SWIGS type research into the new era, so to speak. I had a quick look through the chat, a lot of chat between Peter and others. I don't spot a particular question. So while I'm waiting for any further questions, just maybe you touched on this, but within Gorgon as a piece of code, are there specific areas that you can see, modules, if you like, that need improving and can be improved?
Yeah, I mean, so one thing that we are thinking about a lot is the nature of the grid. So we typically run on a fairly regular grid, and we've been doing quite a bit to develop different shapes, so either stretched or other geometries, because that would it will give you better resolution, for example, near the Earth. The thing is, actually, but again, it's sort of tricky because, for example, it might be that you need resolution where you don't expect it, for example, in the tail. And so trading that off is quite tricky. The other thing that we have been thinking about is going beyond MHD. And so this is a very long-term prospect, but nevertheless, there are various ways to do it. And in particular, in the laboratory plasma, again, we have been looking at a little bit. So that's also another goal. And then beyond that, I think there's a number of things specific to MHD modeling of the magnetosphere that we could also add. So there's loads of stuff to do, and
yeah, I can imagine.
It's really very interesting. Yeah.
Okay. Well, hopefully there'll be some questions and thoughts will pop up in the chat for you to have a look at for now. But thanks, and we'll move on to our final speaker of the session and our meeting today. Our final keynote speaker, Chigomezyo Ngwira, who's presently a senior research scientist with ASTRA in the States and also an adjunct research scientist at the Catholic University of America in Washington, DC. I know Chigo because he's previously worked and probably still does work with Antti Pulkkinen at NASA, and also he did a PhD at University of Cape Town with Professor Trevor Gunt, a well-known power engineering expert with an interest in space weather. And today, Chico's going to talk to us about geomagnetically induced currents in the United States, past, present, and future efforts. And Chigo, I'll let you know when you've got about 5 minutes left. But you're welcome now to share your screen and take it away.
Thank you. So let's see, which one is my desktop here? Oh, Zoom is asking me some things I've never seen before.
There should be at the bottom of the window. There should be a green.
I see the share screen, but it's asking me for preferences. Where did I go?
If you click that, it should start to share your screen. It's asking you for preferences.
Yep, it seems something is blocking with this, which has never happened before. Just a little bit. Let's see.
I'm not sure if any of my colleagues are able to understand. Are you having sometimes when you try and share screen, it will often ask you to select which window you want to share?
Yes.
So you just double click on your presentation.
Okay.
Let's try that.
There we go. So I see something now. Do you see it?
We can see it. You can put it in presentation mode.
Great. All right.
And off you go. Yeah.
Okay. So let me make this full screen. Okay, so thank you very much for inviting me to give this talk. I'm going to be talking about geomagnetically induced currents in the US, particularly trying to look at some of the past work, the present work that is being done, and also looking at what future works need to be done. So I know that this presentation has been put together with the help of so many other people. And so just to appreciate my collaborators who are listed here for their contribution to this presentation. So as Alan has said, I'm with the Atmospheric and Space Technology Research Associates, commonly known as ASTRA in Colorado. Okay. So this is just probably a summary of why we are here today. It's because of space weather and the impact of space weather on the different technologies and also on human life. And I won't spend much on this slide because I think most of us have seen this slide before. And just to emphasize that we are particularly interested in the GIC problem, which is highlighted down here. I should mention that you might be hearing strange noises as my presentation goes on. I'm on double duties, parenting and presenting, so forgive me for that. So when it comes to geomagnetically induced currents, so this is the picture that we are looking at. So we have eruptions at the sun that then travel in interplanetary space. It's the interaction of this plasma, the CMEs, we call them, with the Earth magnetosphere that then leads to changes in the current system within this magnetosphere. These currents then induce this electric field on the ground, which then drives the currents through the ground system, such as power grids. You're talking of oil and gas pipelines, and may also have effects on telecommunication systems. So it's that rate of change of magnetic fields then which is responsible for the induction of the electric field coupled together with the ground conductivity. So in the whole GIC problem, it's not just the magnetic fields, but also the coupling with the ground. So the resistivity of the ground, the conductivity, plays a critical role in establishing this electric field. So we can split the whole GIC problem based on the explanation I've just given into two parts. Basically, you have the geophysical part, which has to deal with the solar wind magnetosphere ionosphere coupling and the geology of the ground. And then you have an independent part, which has to do with the engineering. And this has to do in turn with the GIC flow on the power systems. Now, my talk today is mainly focused on the geophysical aspect. Specifically, I'm just going to be talking about the magnetosphere ionosphere coupling. So I'm not going to talk about anything that has to do with the geology. But if you are interested, there are a couple of papers that I would refer you to that look at some of the geology work that is being done specifically in the United States. Especially in these times that we are trying to move away from the 1D to the 3D conductivity models, which almost about 60 or 70% of the USA has now been mapped under the US RA project. So you have 3D conductivities, mostly for the northern section of the United States. So in the past, we have looked at work that highlights some of the extreme events that we have experienced. So we did a study starting in 2012, was published in 2013. And the work was focused on looking at these extreme storms that we have experienced between I think it's 2000 to about 2015 or so. And so what you're seeing here is the maximum electric field computed at different ground stations. That these are intermagnet stations. And so we use the uniform ground conductivity to produce these electric fields. But what this graph shows, the electric field, maximum electric field for each storm. So there are 12 storms all in one in this graph. And then on the bottom axis, we have the geomagnetic latitudes. And so we see this characteristic of the electric field, but it can also be seen if you were to use just the magnetic field or the BDT. And two things in particular do stand out here. And what it is we have this region both on the southern and the northern hemisphere, but it's more pronounced in the northern hemisphere because of the large number of magnetometers in these locations. And so where the electric fields jumps by almost an order of magnitude as you move from the mid latitudes into the high latitudes. And the same on this side. And then also we have this region, which is in the equatorial region, where you have this very sharp enhancement of the electric field because of the equatorial electrojet. And this one on the high latitudes is because of the auroral oval. So we believe that the current systems here, when you're under the aurora, increases significantly. And this is what causes this jump here. So this is a characteristic that was previously reviewed by work that was done by Antti Pukkanen and others, and then we confirmed this and also confirmed what were the driving mechanisms for this region over the equatorial locations. In this same study, so what we did was to look at the DMSP energy flux and try and locate where this boundary was. And what we found was actually that this boundary was consistent with the data that we were seeing in the DMSP. So you have the poleward auroral oval location, and then you have the equatorward location. And we see that these locations, as you see it in this graph, and if you compare to the previous graph, are actually consistent in their locations. So this was a confirmation of the work that we were doing using the electric field. And then as we moved on from this work, the biggest question that most people ask is, how severe can space weather get? And if you go back in history, we have had significant geomagnetic activity, but then none of these geomagnetic storm ever stands out to the Carrington event, which has been the largest observed event. And so what we did was to try and do some kind of reverse engineer based on the data that was recorded at Colaba in India. There's one single complete magnetogram over there. And so we looked at that magnetogram and tried to create a storm scenario that would reproduce the magnetic field at Colaba. The end result was a paper in 2014, which we called the Extreme Carrington Simulation. And so what you can see in this graph is that in the top section, it's more of the same plot I showed earlier, which has the maximum electric field and the geomagnetic latitude. But in the bottom section, what we did is, because the model that we use, we had to change the model settings in order to accommodate the extreme conditions that we were simulating in terms of the solar wind drivers. So we simulated the Halloween storm and then compared the Halloween storm to real data. And that's what you see in this bottom panel. So there's the simulation and then there's the observations. And you can see that the observations and the simulation match very well. Of course, here in the equator, this is not reproduced. The data shows this enhancement, but of course, MHD models do not have that capability to produce the enhancement in the equatorial electrojet. So we have these locations, which is the geomagnetic boundary, which is the high latitude locations. But then when you compare it to the Carrington simulation, you see that this boundary location moves to much lower latitudes than we have experienced before. And so this was really something interesting, because if you compare these locations and look at the historical data, you actually see that we were able to produce close to what has been published in our literature that talks about the Carrington event and where the aurora was seen. So this is very, very low latitude. And this means that if it was for the USA, then the entire USA would be under this aurora phenomenon. So this would expose a lot of the lower latitude power grids that are not used to experiencing such huge currents. So it increases that risk. And so it's really a major concern. So since I've moved on from Goddard, although I'm still in touch with Auntie and the rest of the team, they've continued to do some of the work, extending on the work that we had previously done with Auntie. So some of the works that they've been doing primarily focused on the storm dynamics, of course, and looking at the extremes. So the major interest, of course, again, is this auroral oval and the movement of the auroral oval. How far can it extend to the lower latitudes? So we've been looking at this southward or equatorward extension of the auroral oval, and then also this localized electric field. Now, I'll talk more about this localized electric field enhancements in a later slide. But of course, how this phenomenon manifests during these low probability storms, we know that the most significant of these storms are very rare storms. So there is high impact these storms have, even though they're very rare. An example is just the March 1989 storm that happened to have crippled the Hydro-Quebec network. So some of this work of course, is based on simulation. And recently, Sean and Antti published this work, which shows how the extreme solar wind conditions or how the MHD models respond to these extreme solar wind scenarios. So they have done some more recent work on this. In addition to that, they still continue to look at these historical storms, like the really strong storms like the Carrington event. And also there's been some simulation work done, and there's recent work that has just been published, which you can look at. This is 2020 and then 2021. Another group, this is Danny Welling, who is now at University of Texas in Dallas. They've been doing some extreme storm analysis as well, and they recently published this work, which is the perfect storm scenario. Now, this work is based on some hypothetical perfect CME that was estimated by Turutani and Lakina in 2014. And so what you see on the left here is this solar wind data that they have used to produce, to perform these simulations. And so there's this very strong jump. You see very strong IMF BZ. I would say almost a relatively common density, but also this very rare speed. And in these simulations, after performing these simulations, what they found is that the BDT values exceed this 30 nanoteslas per second at low latitude, as low as 40 magnetic latitude. So for these latitudes, that's very extreme conditions. And then there was this erosion of the magnetopause with very strong Birkeland currents. So this is the region 1 current to intensify the DBDT response. These values have surpassed what we have recorded in previous storms. So these new upper limits of the thresholds extreme show that we have these very extreme GICs that can occur when you look at these very extreme conditions. So here is the plot that shows the magnetic fields that were reproduced or that were simulated for northward IMF conditions. You can see here in the top 2 panels. But then you also see that for southward BZ, you have really very strong magnetic field perturbations on the ground. Right? And then I have mentioned that I would talk about these localized electric fields. And what we're seeing here is a scenario where we're looking at the magnetic field for the Halloween storm. And what you see in here is just magnetometer data, and we're looking at these amplitudes of the magnetic field perturbations at these different locations. Just a moment. So these different locations, and what we see is that in this location in the northern hemisphere, I think this is Greenland, you see a very extreme magnetic field perturbation. But then this magnetic field perturbation, you see that it stands out from the rest because there's very few magnetometer stations that have a similar amplitude. So the interest now is to find out or to try and learn what causes these extreme conditions to be localized, because we have seen that it's not just the Halloween storm. Most of the severe storms tend to have this similar signature. We did a study in about 2018 where we're looking at similar cases. And what we did was to look at data from Alaska. So we looked at the different magnetometer stations, and you see in here on the left, this is just an electric field. And you can see very strong electric field in this time interval on March 9, 2012. And then on the right, this is the data from one of the Themis spacecraft. This is Themis D. And during this very time of this strong electric field amplification, we see that there is something that is happening in space as the satellite, at the satellite location. And we see these strong changes in the magnetic field, which is a dipolarization. So we believe this was a strong substorm that led to these changes on the ground. And from the same storm, you see that if you looked at the BDT spatiotemporally, you see that at this moment on the left, that's before the substorm. And then if you look at it on the right side, that is the time, right at the time of the substorm or immediately after the substorm. And you can see this very strong enhancement in Alaska, which is very highly localized. And so this was a substorm signature, very highly localized. So in this case, we found that the substorm location was mapped to a very specific location, which caused this localized effect. And then we also looked at these equivalent ionospheric currents for the same storm. And these maps are produced by James Weigand of UCLA here in the USA, University of California. And what we found, again, if you look at it, before this substorm, you can see the currents is not very structured. But then after the substorm, you see this very structured effect. And this is a very strong current system that has built up, more specifically here in Alaska, where you see the amplitudes are much higher. And in the bottom panels, you see the upward and downward currents. And the one thing that we found that is really interesting to note or to really outline is that these very strong currents that we see, they actually lie in the border of the upward and the downward currents. You see that in this, where there's the red and blue, right in that boundary is where you're seeing this very strong current system. So moving on from these works that we've been doing, there's also been more recent work that has mostly emphasized like the machine learning aspect. So I'm going to talk about these works. This is the CHESS project. This is the PI is Ryan McGregor, who is also part of ASTRA team in Colorado. And the CHESS project was NSF funded. The project just came to an end very recently, but the work was more focused on the ontology and also on the machine learning and bridging the gap between the different disciplines that exist in the whole space weather chain. So you have the solar physics, you have the space physics, you have data science, you have the engineering aspect. So all those aspects being brought together make up the CHESS project. And so there's been some success with the CHESS project. There's been a lot of work that is being published. So they've made, under this project, there's been a lot of significant progress. New understanding of the quiet times. There's new connections between GICs and magnetometers that have been produced from this work. And also the machine learning models can better predict these variations that we've come to know.
I'm so cold.
No, I'm not cold. Can you leave now?
I'm so cold, Daddy.
I'm sorry about that. Okay, so there's also machine learning work that has been going on in the University of Alaska. And so this is a project that is funded by NSF. And this is, the PI is Yunji Kona. And what they're trying to do is to learn to train these neural networks so that they are able to predict DBDT and be able to produce predictions for Alaska. And so once matured, these machine learned DBDT models will be used for advanced GIC warnings. There's also this Pathfinder project, which is part of the same project, making data available. So they're working with the power utility in Alaska, and the power utility is going to make the GIC data available to the research team, which is a very good thing in that you'll be able to understand really these GICs if you couple together the space physics data, which is the magnetometer data, and also the power utility data to understand the GIC flows and the coupling of the space weather to the power systems. And also there's an aspect of this project which has to do with broader impacts and teaching students and also building magnetometers, and these magnetometers are being installed to be able to monitor the space weather conditions over Alaska. On the same project, Yunji Corner, they are, I would say, funded together with the University of New Hampshire. And so the work is being done as a collaborative work. And so the work in University of New Hampshire is trying to compare these neural networks, also predicting the crossing of the thresholds using this data that is predicted by the neural networks. So it's more of just machine learning and trying to produce DBDT and looking at the thresholds and then establishing these metrics that can then be used to see how well these machine learning models or the neural networks are doing in terms of the predictions. I think some of you may know Jennifer Gannon. Jennifer Gannon has been for a while now running this project, which is NSF funded, and they're installing new magnetometer stations across the USA. But also not just installation of these magnetometers. This work is also collaboration with Electrical Power Research Institute, EPRI, to see how this can help to improve the prediction of GICs. So this is modeling and then validating the GICs as observed in the power systems. So you can see here how they have produced they have produced the GICs and then compared to the observations. And there's really a very good match by using magnetometers that are much closer to the station than picking a magnetometer that is really very far away. And you may know that right here in the USA is very big, but then there's only very few magnetometers, as you can see on the left side. There's only very few magnetometers.
Chigo, you have 5 minutes. You have 5 minutes, Chigo.
Okay, all right, thank you.
Thanks.
There's very few magnetometers in the USA, so these magnetometers need to be supplemented for any meaningful modeling to be done. So recently I've been funded by NASA to perform some work, and this work is trying to help NOAA, which is the official US government institution or agency that is tasked with dissemination of space weather information that has to do with the Earth. And so NOAA has produced this GIC map. But the thing is that the GIC map or the geoelectric field maps that they're using over continental US lacks these magnetometers because they're using the interpolation technique. And the interpolation technique, the more magnetometers you have, the better the interpolation fits. And so because of the sparsy nature of these magnetometers over the USA, this is a critical limitation for this technique. But there's many other magnetometers in the USA. These are stations that have been installed with science grade magnetometers. And what we're looking at is incorporating those magnetometers into the interpolation technique and then helping NOAA to produce new products that will use these many magnetometers for the prediction or for the operation services. So in addition to that, we aim to do validation, and also we want to support NOAA by building these new products. Another aspect of our funded work is to perform these new simulation studies, because we want to understand how the extreme storms will impact the US power grid. So we're going to do these extreme simulations and then produce the electric field and model the GICs in partnership with EPRI and see how the US power grid would respond to these extreme storms. So this is the geoelectric field map that NOAA produces. You can see all these pink dots represent locations where the interpolation is being done. And then the white squares is where you have the actual magnetometer stations. So we're going to use this spherical elementary current system techniques to try and supplement NOAA's work. And so we're going to extend this, because right now it's more focused to the northern parts of the USA, but we want to extend it so that it covers the entire USA. And then this can be also a tool that we can use to monitor the auroral boundary, which is the major concern for extreme storms. And you can see in this lower part, this is for the during the March 2017 storm, the St. Patrick storm, and you can see that this current system extends much lower when you have these severe geomagnetic storm conditions. So in summary, just to say that there are several groups that are working on different aspects of the whole GIC problems in the USA. There's teams that are working on just analysis of historical events. There's MHD simulations. More recently, we have had an uprise of the machine learning techniques. And also to supplement all these work is the need for installation of new instruments. So there's been a lot of magnetometer deployments that have been going on. And through this new funding that we have received from NASA, we're focusing on understanding the extremes and also improving operational tools that can be used by operational agencies like NOAA. And just lastly, I would just like to highlight that the ISWAT COSPA Geomagnetic Environment Cluster, this is a group that is cutting across barriers because it's an international group and it's tasked to look at these different geomagnetic environment problems. So recently there's been a call. If you could submit your works to Herman or to myself, and we want to come up with a new review paper. And so we are collecting the works that have been done by different groups from many different countries. And we're going to incorporate all these works into one review paper. I think it's a long time that we have ever seen a paper, a GIC paper, review paper. So this could be a very good thing for us to know where we're coming from and where we are and where we're going for the future. And with that, I'll say thank you very much.
Okay, thank you, Chigo. Thank you for giving us a really interesting insight into current US developments, some of which certainly is news to me and may well be to my colleagues in the audience. But it's a very exciting time. There's a lot of developmental stuff happening, especially around machine learning. I don't know if you mentioned about magnetometers and it being a very sort of sparse array within the United States. Do you have any idea about how many additional variometer systems might be funded to be included in this work?
I'm not sure how many magnetometers Jennifer has been funded to install, but I would think it would be in the range maybe of 5 to 10 or something like that.
Yeah.
But just on the ground, if you take away the actual intermagnet observatories over the USA, there is roughly about 20 to 30 magnetometers that are installed as science-grade magnetometers, but they're not just observatories. So NOAA is missing out on all these magnetometers because they're only depending on the intermagnet stations.
Yeah, I know. There was one, I think it's a comment in the chat channel from Maria Wallach. She says, interesting talk, Chigo. You said that during a Carrington-type storm, the electric field can reach latitudes of 40 degrees. But she comments that you don't need an extreme event like Carrington. We have observed the ionospheric electric field expanding to 40 degrees during storms of the most recent solar cycle. That's a really interesting comment, Maria. And there's a link there, presumably, to a paper on this. So it's just an observation I think Maria's offering. Maria, if you want to follow up on any of this, please do.
Yeah, thank you. Yeah, I'll certainly do. Thank you very much.
Yeah, it's very good. Oh yes, and there is a question, so she's ahead of me. She said, for the substorm event that you've shown, how well does the electric field correspond to magnetometer measurements in quantitative terms?
Okay, so one thing I should point out is that for the electric field, we've used I would say, a uniform conductivity model. We were just interested in looking at the spatial variation. So it's not really a representative conductivity model that we would make that quantitative analysis.
Okay, yeah. There's a couple of comments from people applauding you for being able to present while doing parenting duties at the same time, and I can only agree with that. You did a fantastic job.
These guys were sleeping, now suddenly just got up. So
oh, we've got experience of that. I've got colleagues who have the similar problem. They always normally sleep at a certain time of day, and then suddenly it had to be this one time they all wake up. Yeah, I know. There's another question from Matthew Allcock. I don't know if you were around when Matthew was speaking on behalf of EDF Energy. That's one of the power companies in the UK. And he's asking, has the US had any transformer damage in the past due to extreme GICs that you know of?
Yes, there has been. During the 1989 storm, there were transformers that have been alleged to have been blown out in US, somewhere in New York. So there were some transformer damages over there.
That's my understanding as well. In fact, I think it got.
That's the only event that I know of. I don't think there's any other event apart from that.
Yeah, in fact, it was obviously a high voltage transformer, but it was at a nuclear facility on the East Coast, I think.
3 Mile Island?
No, I don't think it was. Yep. Matthew Wilds has commented, a Philadelphia power company lost a transformer. Matthew, was that during March 89 storm? Maybe you could comment in the chat. Yes, thank you. Any other questions for Chigo? I'm not seeing anything.
I've been promoted to be able to speak, so maybe I can continue my question. It's Matt Allcock from EDF speaking here.
Okay,
thanks for the answer about the transformers that were damaged in 1989. Do you know if that was responsible for any blackouts, or was it kind of a redundancy in the system and didn't lead to any effects?
There's never been mention of any blackouts in the USA during that event. So I'm assuming they had some kind of backup transformers or backup power.
Okay,
it's only in Canada where you hear that there was this blackout.
Yeah.
I don't think there. Oh no, there is one. Matthew Wild is commenting that there's very little redundancy. I think he's. Yes, this is with respect to the Philadelphia Power Company lost a transformer. He's saying very little redundancy. They had to wait 42 days for a replacement. And in fact, that was something that came up in chat earlier on this morning when one of our attendees pointed out the kind of long lead times it takes to replace the transformers because of size, and they're very bespoke. They're developed for specific locations under certain constraints. So yes, that is an issue if you were to lose, let's say, more than just one or two. Okay, I think that's the end of the questions. Thanks again, Chigo. We are 25 past
pleasure,
3 local time. We do have to finish sharp by 3:30, so it doesn't seem we've really got a chance to get into a discussion as such. That's why I'm still got an eye on the chat just in case something comes up. But I think at this point it makes more sense if we bring the meeting to a close. And I'd like to thank all of the speakers today for some really excellent presentations. The poster presenters as well. I hope you enjoyed the Gather Town experience. I'd like to thank my co-organizers and therefore the chairs from this morning, and of course the Royal Astronomical Society for hosting the meeting. A summary of the meeting will appear in print in the RAS's Astronomy and Geophysics journal as normal. And we'll be in touch with the speakers to help us put that together as a record of their presentations. What else do I need to tell you? This has been recorded, and we will try and find out at what point and in what manner you'll be able to get access to recordings and presentations. I'll just pause to ask my co-conveners if there's anything else I should be mentioning at this point, in case I've forgotten something. No, I'm getting a no. Okay, in that case, I think we're done, everyone. Thank you for joining, and have a good afternoon, good weekend. And I hope at some point soon we can actually meet in person. It's been a long time, and I don't know about you, but it's pretty much a year since we went into lockdown. It must be the same for most people. I'll ask my co-conveners if we actually need to stop the recording or whether the RAS will do that. But at this point, I think we just say goodbye and thank you again.
Thanks, everyone.
Thank you. Bye.